AMOC.
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 The Atlantic Meridional Overturning Circulation.
The Atlantic Meridional Overturning Circulation.
Atlantic Meridional Overturning Circulation.
The Atlantic Meridional Overturning Circulation.
Atlantic Meridional Overturning Circulation.
The Atlantic Meridional Overturning Circulation.
The Atlantic Overturning Circulation, or Meridional Overturning Circulation as it is called in short, AMOC. Meridional just means in north-south direction.
Atlantic Meridional Overturning Circulation.
AMOC.
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 Hello, my name is Vivianna. I want to welcome you to the Vita TV special on the AMOC. The AMOC is a huge ocean current that brings warm water from the equator and helps keep northern Europe warm. There are concerns that climate change is causing the AMOC to slow, and this risks bringing on an ice age in Europe. In this Vita TV special, we will dive deep into the science of the AMOC, with videos from Sabine Hossenfelder, Paul Beckwith, Stefan Rahmstorf speaking at the Arctic Circle, David Borlace from Just Have a Think, and the National Oceanography Center. Please enjoy learning about the AMOC, the ocean current that can change the world.
AMOC.
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 We hear a lot about climate change increasing the average temperature of the Earth, so-called global warming. Well, ironically, amidst all that warming, some places are getting colder, and some places are likely to get even colder still. A string of scientific studies over the past few years have indicated that the threats to the stability of the AMOC have been greatly underestimated. The name AMOC refers to the Atlantic Meridional Overturning Circulation. That's a big name for a very big ocean current that moves huge amounts of heat around the world, and importantly, helps keep Western European winters mild. The name Atlantic Meridional Overturning Circulation comes from its location in the Atlantic Ocean. The word meridional means that the current follows the meridian, which is to say that it predominantly runs along the north-south axis. Overturning suggests that the current flows at the surface northward, then sinks to the seafloor and runs south through the abyss. Because of global warming melting Greenland, the North Atlantic is becoming less salty, and it's the high salinity that fosters the AMOC to sink to the seafloor. The shutdown of the AMOC was popularized in the 2004 movie The Day After Tomorrow. In the movie, the AMOC grinds to a halt practically overnight, throwing the Northern Hemisphere into an ice age. Fortunately, that's Hollywood, it's not likely to happen so fast. Fact versus fiction. Heating begets cooling. It can all seem so terribly complicated. Fortunately, there is an institution that can help you keep on top of the latest advances in environmental science, and to connect spiritually to the living planet that is our life support system. Vita Sapien organization advances a sustainable life philosophy called Vita Worldview and spreads its message through pods. Pods are social networks of people who read, share and practice Vita Sapien's sustainable life philosophy. Read Vita Worldview and join the Vita Sapien movement today.
AMOC.
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 If you've seen the 2004 disaster movie, The Day After Tomorrow, you probably remember the catastrophic effects of global warming, the melting of polar ice caps and glaciers, leading to a shutdown of the Atlantic Meridional Overturning Circulation, a crucial ocean current that regulates global weather patterns. The Atlantic Ocean, with its vast expanse, holds within it a complex network of ocean currents, including the Atlantic Meridional Overturning Circulation, AMOC, which stands out as a crucial player in regulating Earth's climate. This immense conveyor belt of water, heat, and salt serves as a fundamental component of the planet's climate system. But recent scientific discoveries suggest a potential crisis on the horizon. Join us as we delve into the depths of the AMOC, uncovering its mysteries and facing the reality of its potential collapse. At its essence, the AMOC functions as a symphony of movement, directing the flow of water from the frigid depths of the Southern Ocean to the sunlit shores of the Northern Hemisphere. This intricate circulation, driven by the interaction of temperature and salinity, serves as the cornerstone of Earth's climate system. The process initiates with the descent of dense, cold water in the North Atlantic, setting off a downward current that propels warm, salty water towards the poles. This complex choreography, known as thermohaline circulation, drives the engine of global climate, influencing weather patterns and sustaining ecosystems worldwide. Beneath the seemingly calm surface of the ocean lies an impending crisis. Recent studies indicate that the once stable Atlantic Meridional Overturning Circulation, AMOC, is now teetering on the edge of collapse. The ramifications of such an event would be dire, setting off a chain reaction of climatic disturbances with far-reaching consequences. When this collapse occurs, it would unleash profound implications, including rising sea levels, exacerbated global warming, disruptions to marine ecosystems, and disruptions to biogeochemical cycles. Food security would be under significant threat, and highly productive marine ecosystems along the western coast of South Africa and Namibia, such as the most productive system of its kind in the Atlantic, would suffer severe impacts. Europe could face a substantial cooling of approximately 5 to 10 degrees Celsius, while tropical regions might experience intensified heat. Various parts of the world would grapple with severe droughts and increased flooding, exacerbating existing environmental challenges. Moreover, the acidity of the world's oceans would increase, posing further risks to marine life and ecosystems. Evidence from past events sheds light on the potential consequences of AMOC disruptions. For instance, Northern Europe experienced 2 severe winters from 2009 to 2011, which were linked to a temporary slowdown of the AMOC. During this period, heat accumulated in the tropics, contributing to an unusually active hurricane season in 2010. In 2013, a cold anomaly, known as a cold blob, emerged in the North Atlantic, peaking in the summer of 2015. This coincided with heat waves in Central Europe, demonstrating the complex interplay of ocean currents and atmospheric conditions in shaping regional climates. While the cold blob phenomenon bore some similarities to the characteristics of a weakened AMOC, subsequent analysis dismissed any direct causal connection with AMOC weakening. Instead, the transient episode was attributed to localized atmospheric influences. Nonetheless, this event provided valuable insights into the potential effects of anomalous temperature patterns, which could result from AMOC weakening on a larger scale. Even though this particular instance did not originate from AMOC weakening, it hinted at the broader impacts such changes could have on regional climates. In the pursuit of understanding the fate of AMOC, scientists have employed advanced modeling techniques and state-of-the-art technology. Recent research, led by prestigious institutions like Utrecht University, has illuminated the mechanisms driving AMOC variability. Through comprehensive simulations spanning over 2,200 years, researchers integrated the influence of human-induced climate change into their analysis. Within 1,750 years of simulation, an abrupt collapse of AMOC was observed, highlighting the vulnerability of this crucial oceanic circulation system. Key drivers of AMOC collapse, such as the melting of Greenland's ice sheet and the influx of fresh water into the North Atlantic, have been identified. These findings emphasize the urgent need for proactive measures to mitigate the impacts of climate change and preserve the stability of Earth's climate system. From reducing carbon emissions to investing in renewable energy and conservation efforts, the solutions are within our grasp. The time to act is now, for the fate of our planet and future generations hangs in the balance.
AMOC,
AMOC,
AMOC.
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 AMOC. AMOC.
AMOC.
AMOC.
A couple of years ago, I made a video based on a scientific paper from a team at Potsdam University in Germany, led by the climatologist and oceanographer Stefan Rahmstorf. That research found that the Gulf Stream and Atlantic Overturning Meridional Circulation, or AMOC, had slowed down by about 15% since the middle of the last century. A collapsing AMOC was, of course, the main feature of the Hollywood blockbuster The Day After Tomorrow, which, in true Hollywood style, exaggerated the consequences out of all proportion and had the whole of North America under several feet of ice within about 48 hours. That impossibly rapid pace of change is thankfully not going to happen, but it is perfectly true to say that the AMOC circulation has collapsed before. In fact, it's collapsed several times over the course of Earth's long history, and records show that when it happens, it does have a very significant impact on global weather patterns. In an attempt to better understand why our global ocean circulation appears to be slowing down again now, and whether it might grind to a complete halt in the near future, scientists have been searching for evidence of what caused previous collapses of the system to establish whether those same phenomena are happening today. And now one group has published their findings in a new scientific paper. So what's going on? Is it us with our climate warming greenhouse gas emissions, or is it a completely natural process that would have happened anyway? And if the AMOC system is collapsing, how quickly will it happen? And what will be the consequences? So many questions and so little time. So let's dive straight in. Hello, and welcome to Just Have a Think. So what is the AMOC then anyway? Well, Atlantic means, it means it's in the Atlantic. Meridional is just a fancy word for southern or southerly, so that tells us a bit about its direction. Overturning refers to different layers of ocean water rising and sinking below each other depending on their relative temperature and salinity, and circulation is hopefully pretty self-explanatory. Over in the Gulf of Mexico, the water is really very warm indeed, about 24 degrees Celsius or 75 degrees Fahrenheit, and it's moving at a decent pace too, about 6 miles or 10 kilometers an hour, shifting more water every second than all of the rivers in the world combined. That warm water comes across the Atlantic towards Europe, and as it does so, some of its heat is lost to the atmosphere through evaporation. The result of that is that temperatures in my part of the world are, on average, about 10 degrees Celsius warmer than areas at the same latitude across the pond. But evaporation only liberates water, it doesn't take any of the salt. That means the concentration of salt in the remaining current of water increases along the way. Eventually the warm, salty water hits the cold, fresh water below the Arctic Circle, and because it's denser, it sinks and gets caught up in the deep southerly currents that carry it all the way south, around Antarctica, across into the Indian and Pacific Oceans, and eventually back up to the Gulf again as part of the global thermohaline circulation. It's a process that ensures the waters and essential nutrients in our oceans are continually mixed and that heat energy is distributed around the planet. It's a tortuous journey though. A whole circuit can take up to 1,000 years to complete. AMOC is a big driver of the overall system, so if it slows down or grinds to a halt, then the consequences aren't local, they're global. Climatologists and oceanographers like Stefan Rahmstorf tell us that climate change is indeed having an effect on the AMOC system. As we've discovered in previous videos here on the channel, human-induced greenhouse gas emissions and Arctic amplification mean that the Arctic is warming at a much faster rate than the global average. That warming is melting ice from the Arctic Ocean and from the Greenland ice sheet, vastly increasing the amount of fresh water in the surrounding seas. As the water freshens and becomes less salty, it gets less dense and therefore less likely to sink and join up with the deep cold currents. And that slows down the AMOC system. This paper, published in 2018, found that right now AMOC is the weakest it's been for about 1,600 years. A more recent study, published in July 2022 by teams at the University of Bremen in Germany and the University of Sao Paulo in Brazil, analysed sediment cores from water almost 2,000 metres deep at a site to the east of Newfoundland in the subpolar western North Atlantic. Those sediment cores hold hidden information going back thousands of years. Layers and layers of plankton build up over those millennia to provide a chronological database of ocean conditions, a bit like the rings of a tree can reveal what the weather was like in each growth season. In this case, the scientists studied the ratio of magnesium to calcium in a species of plankton with the spectacular name of Neogloboquadrina pachyderma sinistral, or N. pachyderma sin, going back 250 years at a time over 27,000 years. And through the clever jiggery-pokery that modern-day science allows, they use this data as a proxy for historical subsea surface temperatures down to depths of about 150 metres. But N-pachydermous also contains a stable oxygen isotope called delta O18, which can be used as a proxy for ocean salinity over the same period. So now the team had a comprehensive record of ocean temperature and salinity going back far enough to span periods of previous AMOC collapses. The data demonstrated that warming of the waters at high latitudes of the North Atlantic closely corresponded to times of a weakened AMOC and preceded a massive release of an armada of icebergs from Canada and the US into the Atlantic, which caused enormous freshening of the surrounding waters, resulting in the rapid and total collapse of the AMOC system. As I mentioned earlier in the video, we already know that the AMOC system is weakening again now, and we know that the main drivers this time around are an overall warming of the planet's surface and a much more rapid warming of ocean water at high latitudes, causing more intense rainfall, all of which is being turbocharged by human-induced greenhouse gas emissions. The warmer water is melting and destabilising glacier sea snouts in Greenland, which is accelerating the release of enormous volumes of fresh water into the ocean as the melting of the Greenland ice sheet speeds up. In other words, we humans have rapidly created very similar conditions up in the subpolar regions that caused a massive release of icebergs thousands of years ago. Scientists are not projecting an imminent collapse of the AMOC system, but it is potentially a bit too close for comfort. A 2019 article from the UK Met Office found that while a total AMOC shutdown this century is very unlikely, it does remain a possibility. They also say that if the world started taking urgent steps to properly mitigate climate change, then the weakening could be slowed or even reversed. But of course we humans are a curious bunch, aren't we? And scientists have been debating the consequences of an AMOC collapse on modern day society for some time now. In June 2022, another research paper was published that took an in-depth look at those consequences. It was produced by researchers from the University of New South Wales, and it used very sophisticated model simulations that suggested there would be abrupt changes reaching far beyond the Atlantic basin and Northern Hemisphere, stretching right around the globe. In what they call the AMOC off scenario, the researchers found that cooling in the North Atlantic would extend southwards, reaching the northern mid-latitudes within the first 10 years after shutdown, and the tropical Atlantic by year 20, largely as a result of sea surface wind evaporation. The model also showed cooler sea surface temperatures creeping into the higher latitudes of the North Pacific by around year 5, becoming well established by year 20. That North Pacific cooling would eventually cause sea ice to expand in the ocean basin, which would reinforce the cooling as a result of the extra sea ice reflecting the sun's energy back into space via what's known as the albedo effect. By about year 30, the model showed that cooling would start happening in the equatorial Pacific, evolving that region into more permanent La Nina-like conditions. We took a closer look at the effects of a sustained La Nina quite recently. Suffice to say, they're not great, especially for countries like Australia and Africa. Then there's the shutdown of a crucial movement of heat from the southern hemisphere to the northern hemisphere via the great thermohaline circulation that I mentioned earlier. With that switched off, most of the ocean heat stays down south, with the biggest contrast between southern and northern ocean temperatures occurring after about 3 decades. To compensate for the lack of oceanic heat transport, nature turns to the atmosphere in an attempt to balance global temperatures. There's a strengthening of something called Hadley cells in the northern hemisphere, which are pockets of warm air that rise at the equator and move towards the poles. Hadley cells also create the trade winds, tropical rain belts, hurricanes and the jet stream. So as they get stronger, all those events become more extreme as well. The study even demonstrated AMOC connections to atmospheric circulation over the West Antarctic, with indications that the greater retention of ocean heat in the region would bring about an accelerated melting of the ice sheet, with all the catastrophic consequences of sea level rise that I'm sure we're all aware of. Now, there's a big caveat here, and that's that the research team concede that these results were derived from only a single computer model that was set up under pre-industrial conditions. They suggest future work should examine the impacts of an AMOC shutdown under a range of scenarios that take into account increasing atmospheric greenhouse gas concentrations. So once again we find that the accuracy of climatic predictions are only as good as the models we base them on, which means there's still a lot of variation in the detail. But one thing all the models agree on is that an abrupt AMOC collapse would bring about profound changes to the oceanic and atmospheric systems that all life forms on Earth rely on. Nature's got all the mechanisms needed to recalibrate back to equilibrium over geological timescales, of course, so dear old planet Earth will quite happily trundle along for another few billion years or so, regardless of any undulations in the cycles of its control systems. The threat of AMOC collapse is not to the planet, it's to all the species that live on the planet, including we humans. All the indications are that if and when the AMOC does shut down, it will happen very quickly, with consequences kicking in with only a few years, making it almost impossible for an entire global society to adapt in time to avoid catastrophic consequences. Alternatively, we could start taking climate science seriously, stop wasting time in pointless international talking shops, and immediately implement globally agreed actions to eradicate the combustion of fossil fuels, transform our agricultural practices, and provide support for developing nations to grow their economies in a sustainable way. So another challenging one then, folks. No doubt there are some strong views out there one way or the other, so if you feel a burning desire to share your thoughts, then the place to do that is in the comment section below. That's it for this week though. A massive thank you, as always, to our amazing Patreon supporters who help me keep these videos independent and free of ads and sponsorship messages. And I must just give a quick shout out to some folks who joined recently with pledges of $10 or more a month. They are Paul Ferguson, Robert Nistrom, Tom Fulp, David Gomez, Aidan McGrath, Eric Lutz, David Raff, and Andrew Powser. And of course, a big thank you to everyone else who's joined since last time too. If you found this video useful and informative, then make sure you subscribe to stay up to date with future programs. And if you're keen to learn more about issues and challenges like those we've looked at today, then this video is well worth a look too. As always, thanks very much for watching. Have a great week, and remember to just have a think. See you next week.
AMOC.
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 AMOC. AMOC. AMOC. AMOC.
AMOC.
AMOC. There's trouble at sea, and scientists are sounding the alarm that a core ocean current could collapse. Researchers have been battling to work out what could happen and when. But the truth is that despite the headlines, we still don't know what the risks are. And given that a collapse could have huge consequences for weather across the world, we'd really like to know. So what is the latest research showing us, and what can we do to protect ourselves from the seas running amok? I'm Adam, a climate scientist with a PhD from Oxford, sharing what you need to know about climate change. And one of scientists' biggest climate fears is a shutdown of the AMOC. I mean, it's even the plot of the ridiculous movie The Day After Tomorrow, although, spoiler alert, a real-life shutdown of the AMOC wouldn't involve Jake Gyllenhaal literally being chased by the cold. But anyway, AMOC is short for Atlantic Meridional Overturning Circulation, and basically what all that means is this is the Atlantic chunk of the world's vast ocean conveyor belt. To give a sense of just how vast this conveyor is, it would take a blob of water around 1,000 years to travel the length of it. The AMOC moves heat around the globe, and I am talking about a lot of heat. About 1 million power plants worth of heat energy are brought northwards by this immense ocean current. This huge flow is driven in part by heavy salty water sinking in the North Atlantic, but the whole process could get disrupted by fresh water. If a whole bunch of lighter, fresher water were added right at this crucial sinking spot, that could slow the entire current down. And when I say if, that's unfortunately exactly what's happening. One of scientists' main concerns is Greenland. By heating the planet up, we're melting the Greenland ice sheet, and that's dumping huge amounts of fresh water into the North Atlantic. And if this slowed down the AMOC too much, researchers are worried it could suddenly switch off, collapsing to a much smaller flow. Shutting down the transport of all this water and heat through the world's oceans would have huge consequences for the world's weather, which means huge consequences for all of us. We're talking about things like a sudden chilling of northern Europe, disruptions to the tropical rain belts, and a surge in sea levels on the east coast of North America. And all of this would impact where and how we can live and grow our food. An AMOC collapse is an example of what climate scientists call a tipping point, a sudden shift to a different kind of climate for our planet. And the thing about tipping points is they're not just sudden, they're also hard to reverse. So if the AMOC did suddenly collapse and then we were somehow able to reverse global warming, that wouldn't just switch the AMOC back on. It's a bit like getting a dramatic new haircut. Even if you really miss your hair afterwards, you can't just get it uncut, and getting back to where you started will take huge amounts of work. Now, none of this is just hypothetical, neither the deep haircut regret nor the stuff about the AMOC. In fact, climate scientists think the AMOC has collapsed before, most recently as the Earth was leaving the last ice age. In fact, I made a whole video all about the last 1 million years of climate change, which discusses this potential collapse. You can check that out over here. Okay, now before I get to what climate scientists think is happening to the AMOC now, I need to clear up one thing. You're going to see plenty of headlines like these saying that the Gulf Stream could collapse, and that is just not true. The AMOC does contribute a bit to the Gulf Stream, this current flowing up the east coast of North America, but a shutdown of the AMOC does not mean a shutdown of the Gulf Stream. Okay, but what about an AMOC shutdown? The big question is, could this happen? And if so, when would it happen? Well, the short answer is we don't know. And the long answer is, well, this whole video is the long answer. So the biggest thing you need to know about what we know about the AMOC is that we don't know as much as we'd like to know about the AMOC. In fact, we've only been directly observing it since 2004, which technically means our observations of the AMOC are Gen Z, and just as confusing for millennial climate scientists like myself to understand. There's just so much going on with it that it's hard for us to work out what the trends are. That analogy actually works quite well. While some lines of evidence suggest the AMOC is already slowing down, others imply we can't tell yet, but we can't rule out a slowdown. That said, the science generally agrees that global warming will slow down the AMOC this century. So back to that question, could we hit a tipping point, and if so, when? Well, for a long time, climate scientists have figured that a shutdown this century would be a high-impact, low-probability event. Climate scientists talk for unlikely to happen, but really serious if it did. But the more we've studied it, the less confident we can be ruling it out before 2100. And now a study has been published that tries to pin down the date. Let's talk about what the study says first, and then about what it actually means. So the study is called Warning of a Forthcoming Collapse of the Atlantic Meridional Overturning Circulation. And I'm not exaggerating when I say I can't think of a more panic-inducing title to a paper that I have ever read. I mean, whatever the context, the words warning of a forthcoming collapse are hardly a cheerful way of starting a sentence. And the study doesn't get more cheerful from there. Ultimately, it predicts that the AMOC could collapse sometime between 2025 and 2095 if we stay on our current fossil fuel burning path. And let's be honest, this would suck. But we shouldn't assume that this result is true, because this study had some important limitations. What they did is look at patterns in the measurement of the AMOC to see if these patterns looked like they were approaching a tipping point. But remember when I said we've only actually been measuring the AMOC for like 19 years? So the researchers didn't actually look at measurements of the AMOC directly, instead looking at the temperature of the sea's surface as a kind of indirect measurement measurement of the circulation. So the study could easily be missing what's actually been happening to the AMOC all this time. And given how hard it is for us to be sure what's been happening to the AMOC over the past few decades, we should be cautious about any predictions of what's going to happen over the next century. But as the scientists behind the study put it themselves, even with these reservations, this is indeed a worrisome result. And in case you don't read scientific papers all that often, worrisome is about as close to a full-on expletive as you're ever likely to find. Let's put it this way. We used to be confident that the AMOC wouldn't collapse anytime soon, but studies like this are challenging that. It's not like we now know it's going to happen soon, but we know we can't rule it out. And given how devastating the consequences would be for the entire world, we'd really like to rule it out. If you're watching all of this and you're feeling pretty scared because of this new study, well, I feel you. But know this. Everything we know about the AMOC points to the fact that we also know what we need to do to reduce the risks of a collapse. And so let's talk about what we need to do. The first and most obvious thing that we need to do is observe the AMOC as closely as possible so that we can be sure if or when it could collapse. This could provide us with vital time to prepare to adapt to the dramatic changes. Some scientists have even suggested that we could do some kind of geoengineering where we'd kind of try and hack the climate to stop the AMOC collapse from happening. Although it's important to mention that many scientists are extremely skeptical about these ideas and are worried that they could do more harm than good. The second thing we can do is also pretty obvious. Stop doing the thing that is causing the problem in the first place. The slowdown of the AMOC would be caused by the melting of the Greenland ice sheet, which is caused by the heating of the planet, which is caused by the emission of greenhouse gases, which is caused by the burning of fossil fuels. So how about we stop burning fossil fuels as quickly as possible? The world has already begun the transition away from fossil fuels, and we need to rapidly ramp up that transition. And if you're feeling helpless, know that there are ways that you can meaningfully help. You can push for the structural changes that we need from the top. You can take steps to lower your own emissions, especially important if you're relatively wealthy or you live in a relatively wealthy country. And you can amplify the issue by starting conversations about climate change. If you want to make a start, here's 5 concrete things you can do about climate change without looking away from this screen. Okay, until next time, bye. AMOC.
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 AMOC. AMOC.
AMOC.
AMOC.
AMOC.
So I'm on the beach at Frinton, and around. And I want to talk about Ecospirituality and the AMOC. So the AMOC is the Atlantic Meridional Overturning Circulation, which is this giant ocean current that travels around the world, but importantly brings warm water from the equatorial regions up into northern Europe, and helps explain why Northern European winters are relatively mild compared to the winters, for example, on the same latitude over in Canada and the like, where it's frigid cold, gets down to -40 and the like. And it's this ocean current. And over the last few years, there's been a number of science papers that are suggesting that the AMOC could stop sometime in the not too distant future. Potentially this year, more likely 20 years from now, maybe more likely still 40, 50 years from now. But the point is that there's enough uncertainty about the AMOC collapsing that it's alarming. right? And the other thing is, if it does collapse and it stops, they're thinking it could reduce average temperatures around maybe 5 degrees Celsius, which would effectively lead to vast tracts of Northern Europe becoming largely uninhabitable for much of the year, effectively like a mini ice age. So the question is, that's all very scientific and interesting, actually, but how does that relate to eco-spirituality, ecological spirituality? So ecological spirituality is a subset of spirituality broadly. It's that part of spirituality that people feel that is connected into nature, connected into the ecosystem, connected into the seasons and the beaches and the rivers and the wildlife. And reality. It's connected into reality. And the thing about an AMOC collapse, if the AMOC collapses, let's say hypothetically 2 million years ago there was no Homo sapiens and the AMOC collapsed. And the environment changed dramatically. Ice appeared where there wasn't ice before. Marine species left and some came because of the changing conditions. You know, AMOC collapse is just a part of the natural cycle, so it's nothing really to be concerned about. But if AMOC collapses this century, when there are 8 billion people, it's not just Northern Europe will be affected, it's also the tropics and monsoons and so forth. Big global, AMOC collapse is a global phenomenon, let's put it that way. That's going to create incredible changes in ecosystems at a time when ecosystems are really, really weak because they've been hammered by increased temperatures and deforestation and pollution and so forth. And in addition to that is the well-being of the human population that's going to be massively impacted. And so if we're going to talk about eco-spirituality, we've got to ground things in the word eco. We've got to ground it in ecosystems. And we've got to ground it not just in ecosystems per se, but in this broader sort of narrative around humans interacting in ecosystems. It's a big white dog. Came to show me his ball. Yeah, so I guess what I'm trying to express eco-spirituality in the context of human well-being in a robust and healthy ecosystem. All right? Eco-spirituality, if it's just about the eco, misses out on the well-being of humans, except that humans are a subset of the ecosystem. And so this is a really important point, is the extent to which we actually see ecosystem that includes a subset called humanity, or we see ecosystem and alongside that we see humanity, as though we are putting humanity on an equal footing to the global ecosystem. I think the way I'm framing this is to see ourselves as a subset of the greater whole, and the greater whole is the life support system. All right. Now, if the AMOC collapses, that is going to make great changes to the ecosystem that are going to have very negative impacts on the humans. And so if the humans are a subset of the greater system, we can see that overall that the system is going to suffer, because if one part of the system is suffering, that means the whole is suffering. That's another way of looking at it. I don't actually have a clear answer on this question. The other thing is that, back to the spirituality and the eco, is that one part of spirituality is this concept called awe and wonder and amazement. And I feel that when I'm listening to scientists talk about the AMOC. I feel a sense of awe, because what they're doing through their science is they're giving us insights into this extraordinary Earth system that we live in. And that for me is part of that greater thing. So back to spirituality, the idea of spirituality is about being connected to something greater than yourself. And so the scientists that talk about AMOC and research AMOC, and they put probes on the seafloor, and they got satellites measuring the surface, the temperature and the speed of the current. You know, they got they're examining the seashells on the floor, going down the layers to look at the way that the seashells change over time, which gives an indication of the flow of water and the AMOC. And so learning about the AMOC for me is a part of, it's a spiritual practice, because it helps me develop a deeper understanding of this extraordinary Earth system that I feel myself to be a part of. Understanding the AMOC and AMOC collapse issues helps me redefine my purpose, or to define my purpose as somebody who wants to help maintain Holocene-like conditions on this planet. So part of a greater thing, part of the meaning that comes from trying to maintain the integrity of that system and the integrity of our societies. And also the golden rule, this idea of, you know, do unto others as you would have them do unto you, but the Vita version is do unto others and the living planet as you would have them do unto you. So doing unto the living planet as we would have it do unto us means that we don't go and like aggressively interfere with its natural function, right? So the AMOC changes over time because of, you know, various factors associated with orbital wobbles and Milankovitch cycles and a whole bunch of factors that I don't fully understand. But then the humans come along and start injecting 50 billion tons a year of carbon into the atmosphere. That is massively shifting and jarring that natural system. We shouldn't do that, because we wouldn't want nature to do that to us. So that's three ways in which eco-spirituality ties into the AMOC, learning about the AMOC. And also just another thing in terms of being with other people, you know, what are you going to do today? If you're going to gather with a half a dozen of your friends down the pub, what are you going to talk about? You're going to talk about the football, you're going to talk about your pets, or you're going to have a conversation about the AMOC and share your wisdom. Because everybody that comes into, say, for example, this broadcast, okay, is going to get something different from it, or they're only going to see parts of it, or they're going to be disconnected for some bits because they're distracted. And so talk about the AMOC, talk about the Earth system, create a culture around a reverence for knowledge about these things.
AMOC.
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 Atlantic Meridional, overturning circulation, a lifeline vast for many nations, keeping warm Western European lands. Its rhythm beats through ocean strands. Anthropogenic carbon dioxide emissions have thrown this system into submission. Through complex processes, the AMOC slows a fragile balance, the danger grows. The ocean speaks, its voice is clear, a warning sent for all to hear. If currents fade, the world will change, a future lost, a fate rearranged. The ocean speaks, its voice is clear, a warning sent for all to hear. If currents fade, the world will change, the future lost, a fate rearranged. From melting ice to waters fresh, the AMOC faces nature's test. Salty veins now strained and weak, a tipping point, the brink we seek. Storms will rise and seasons bend, a cascade near unless we mend. The Anthropocene has left its trace on every tide, on every place. The ocean speaks, its voice is clear, a warning sent for all to hear. If currents fade, the world will change, a future lost, a fate rearranged. From Celtic winds and morning seas, once brought the west its gentle breeze. But with each ton of carbon burned, the current falters, lessons spurned. It's not too late to turn the tide, to act with care, with Earth as guide. The Anthropocene has left its trace on every tide, on every place. Atlantic, Meridional, overturning circulation, a lifeline vast for every nation. But with each ton of carbon burned, the current falters, lessons spurned. It's not too late to turn the tide, to act with care, with Earth as guide.
AMOC.
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 Ocean temperatures keep setting all-time highs. But in the North Atlantic lies one very mysterious, very creepy exception. It's called the cold block, or the warming hole. And according to climate models, it shouldn't exist today, which means we're missing something. So one researcher got to wondering, did the cold blob exist the last time the planet was this warm? And if so, what happened after it appeared?
Our study is actually probably provides hints regarding our very near future.
Mohammed is talking about Earth's most important heat transfer system, the AMOC, an enormous ocean circulation that redistributes heat from the tropics and southern hemisphere into the northern latitudes. And this global heat transfer is responsible for regulating weather that we rely on to function as a society, especially temperature and rainfall patterns. And the appearance of the cold blob could mean that this vital Earth system is on the brink of collapse. But it might not be so simple. It turns out that there's a hot debate in the scientific community about the AMOC. And in this episode, we're going to get to the bottom of it. Because although there is debate, what most scientists agree on is that an AMOC collapse will change our world dramatically.
Once the climate warms enough, we could hit a tipping point where very suddenly and very catastrophically, this AMOC current could collapse.
The AMOC brings warm, salty water from the Gulf to the North Atlantic, where it sinks, bringing cold, deep water as far south as Antarctica. This exchange keeps temperatures warmer in Europe and milder in the tropics. But dramatic cooling in Europe probably isn't the biggest impact of an AMOC shift.
Very worried about future changes in rainfall and water availability. During times when AMOC is strong, the northern hemisphere tropics and monsoon regions are generally stronger and wetter.
This, scientists say, is because the AMOC influences the intertropical convergence zone, which is the belt where trade winds meet, forming regions of heavy seasonal rain on either side of the equator, known as monsoons. It's really hard to imagine how many people a sudden shift in monsoons would impact.
Over half the world's population are impacted by them. And so really understanding how those could potentially change is really critical.
That's because as the AMOC slows, the northern hemisphere cools. That cooling shifts the tropical rain bands south, and the monsoons effectively miss regions that count on them for up to 90% of their yearly precipitation, directly impacting food security for over 2 billion people. So with so much on the line, what does the scientific community say?
There are a number of studies that really suggest that the risk is much larger and much closer, actually, with lower levels of warming than we have previously thought.
Most models do predict an AMOC weakening before the end of the 21st century. Some by up to 46%, even in low greenhouse gas emission scenarios, and 55% for high emission scenarios. And some find a collapse by mid-century is possible or even likely. So that's just a few decades away. But there are also scientists at very reputable institutions who declined our interview requests on the subject because they don't believe there is convincing evidence that the current is weakening. So what's going on here? Well, the AMOC is hard to study. It's variable from year to year, so even though a slight slowdown has been observed in the last 2 decades when scientists began directly observing the current, there isn't enough data to determine a trend. And even this slowdown isn't particularly clear. But there is a third way to study the AMOC, and that's by looking at paleoclimate data, or the study of Earth's past climate.
Paleoclimate, in my view, is really critical to understanding the future of Earth's climate, because humans have only been recording climate with instruments and satellites for decades to maybe like a couple of centuries at most.
Using clues buried in snow, ice, marine sediment, and one very unexpected place, which we'll get to in a bit, researchers can put together an incredible history of Earth's past climate by literally measuring cores of the Earth. But getting the data for paleoclimate research is easier said than done. We visited a scientist at Oregon State University who studies ice cores found miles below the surface.
This sample came from about a mile deep in the Greenland ice sheet.
Since ice is so thick, there are thousands of samples that have to be measured, and all of them are cut by hand. Once the ice is cut, it's taken to the lab where each sample is measured.
After we cut the ice samples, we put them in a little flask. That flask is mounted to our vacuum line, and we pump out all the air, we close it off, and we melt the ice.
Christo is measuring the methane concentration in these ice samples, trying to understand past AMOC collapses. To do this, the ice sample is refrozen so that the ice is at the bottom and the air is at the top. He then measures that air.
Once we find the methane spike, we know exactly where we are in time.
By cross-referencing paleoclimate records, scientists are able to confidently reconstruct past climate events.
There's a one-to-one relationship between all these different things: greenhouse gases, temperature in Antarctica, temperature in Greenland, rainfall in the tropics. When the current is on, we know that the monsoons in India and China are very strong. This means there's going to be more wetlands in those places, and wetlands are exactly the thing that produce methane. That's the relationship between methane and this AMOC current. It runs through the monsoons.
Which brings us to caves, the best way to study the Earth's past hydroclimate.
Primarily we use stalagmites in our research. They form on the cave floor as water is dripping, is precipitating calcite layer by layer. So you get these really beautiful long stalagmites that are effectively a history of groundwater chemistry.
By measuring oxygen isotope ratios, which tell scientists the past temperature and rainfall conditions, Kathleen is able to see abrupt shifts in rainfall patterns. This allows her and other scientists to understand AMOC impacts and reconstruct past climate events like an AMOC slowdown or collapse. Earth has 2 major modes: glacial and interglacial periods. Currently, we are in an interglacial period with a warmer, more stable climate. But looking at the last ice age, which is the last glacial period, may actually foreshadow what's coming our way.
One of the reasons we're so concerned about this potential collapse of the AMOC is that we actually have examples of it. During the last ice age, we have at least 25 examples where the AMOC actually collapsed.
25 different collapses during the last ice age is an average of once every 5,000 years. So according to Earth's paleoclimate record, an AMOC collapse in the near future is plausible. And since the last collapse was almost 12,000 years ago, maybe we're due. Each on-off event is world-changing for plants and animals who live through it. When the current collapses, temperatures drop. And during some periods while the AMOC was off, ice sheets reached as far as New York City, northern Spain, and Paris. Christo's ice core study found the average temperature changed by 20 degrees Fahrenheit in the Greenland ice sheet within a few decades. When it turned back on, it raised by nearly the same amount. That type of temperature change in such a short period of time would be catastrophic for humanity and cause ripple effects all over the world.
AMOC were to collapse, during the winter, the North Atlantic would just be covered in sea ice. So within a decade or two, all of a sudden, that climate could shift from a more maritime climate that London has today to a very cold winters continental climate that Moscow has.
So this proves that the current is fundamentally unstable and certainly can collapse. But everything we've been talking about happened during an ice age. What about the last interglacial, when Earth was around this temperature? Well, 128,000 years ago, the Earth was 1 to 2 degrees warmer than pre-industrial times, which is a similar temperature to today, maybe slightly warmer. So it's a pretty good comparison to today's climate. Remember the cold blob that climate models say shouldn't exist? Well, it's there today because so much ice is melting in Greenland. That melted ice winds up in the North Atlantic and makes the ocean less salty. And that salt is what drives the northern leg of the AMOC. Lighter, fresher water doesn't sink. It floats, blocking the overturning current and cooling the surface temperature. So researcher Mohammed Azad decided to see if that cold blob existed during the last interglacial because he wanted to understand the consequences.
We found a warming hole during the last interglacial period. And this has very important implications for our understanding of the sensitivity of the system.
He analyzed marine sediment from the ocean floor to understand the salinity and temperature of the northern Atlantic during the last interglacial.
We found significant cooling associated with freshening and slowing down of the deep water formation in the Nordic seas. Warming climate and subsequent melting of ice could slow down the Atlantic Meridional Overturning circulation.
Mohammed found a slowdown or weakening of a critical part of the AMOC during the last interglacial after a blob formed. So what does that tell us? Well, during the last interglacial, the cold blob was bigger than ours today, but the planet was a bit warmer. Under our current greenhouse gas trajectory, we're likely to see temperatures close to 3 degrees above pre-industrial times by 2100. So if we warm a full degree Celsius above the last interglacial, we melt more ice and risk a slowing or even collapse of the current.
The fact that the AMOC is going to be slowing down is really what we'd expect based on simple climate physics. That's not the question here. It's really a question of how much is it going to slow down and how quickly, because that's going to determine the human impact.
The history of this current shows how likely an AMOC slowdown or collapse really is. But there is some hope here. The last interglacial period, which is much more comparable to our current climate than the last ice age, probably saw an AMOC slow down rather than a full collapse. So whether the AMOC slows down or reaches a tipping point and collapses may very well depend on how much we warm the planet through fossil fuel emissions in the next few decades.
The reason we're trying to keep warming below 1.5 or 2 degrees is exactly these tipping points. As we exceed those 2 degrees, the chances of hitting one of those tipping points really grows, and we could hit these unexpected, catastrophic, sudden changes that we want to avoid at all costs.
Although a weakening of the AMOC may be reversible, there would still be far-reaching impacts. It would get colder in Europe, and the monsoons would shift. But if we lower our warming, the AMOC could turn back on within a few decades. However, a full collapse would leave the AMOC in its off mode for hundreds or thousands of years. One thing's for certain, we must lower our carbon emissions to prevent negative impacts like changes in temperature, storm patterns, rainfall, and food security. Whether we realize it or not, the AMOC and other major ocean currents have such a huge impact on how we live our lives. And to me, that's worth all the heavy debate and continued research on this topic. But I'm curious to hear your thoughts. Do you think the AMOC is headed towards a full collapse? If so, what are some solutions you're excited about to lower our carbon emissions? Let us know in the comments below, and see you next time on Weathered. Hey guys, we want to hear your feedback. Every year, PBS Digital Studios sends out an audience survey which we use to help understand what you enjoy on YouTube and what you would want to see us make more of. You also get to vote on new show ideas, so it'd be great if Weathered fans were well represented in the polls. There's a link in the description below.
AMOC.
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 I've come to think of videos like this as my broccoli videos. It's the stuff that's on your plate that you know you should eat because they say it's healthy, but if you're being honest, it's not what your heart desires. Today's piece of broccoli is this. Every day we're inching closer to a new ice age in Europe because of the collapse of an ocean circulation that's keeping us warm. There are now multiple lines of new evidence saying that this is closer than we expected. Yes, I'm talking about the Atlantic Meridional Overturning Circulation, AMOC for short. That's a current in the Atlantic Ocean which transports warm water from the equator towards the poles. This keeps the water in the North Atlantic warm, and that warms up the air. It's the major reason why temperatures in Middle and Northern Europe are so mild. If the AMOC were to stop, temperatures in this part of the world would significantly drop up to 5 or even 10 degrees Celsius on average. In case you quite like the idea that my mouth will freeze shut, it's not a solely European problem. It'll globally shift precipitation patterns, leading, among other things, to higher temperatures near the equator and more rain in Australia. Probably because no one really knows what it happened. What we do know is that a lot of plants and animals would suddenly find themselves in the wrong climate zones. How high is the risk? Well, in its latest report on the matter, the IPCC concluded that the AMOC will very likely weaken over the 21st century with high confidence, although a collapse is very unlikely with medium confidence. I don't know what that means either, but I believe it means that the average probability for the collapse is small, say 10%, but it has a large spread, so it could be anything between 0 and 50% or such. I wish they would just write down numbers rather than this word salad. In any case, that was in 2019, and since then evidence has piled up that not all is well with the AMOC. One piece of evidence comes from a 2023 paper that looked at temperature fluctuations in the Atlantic Ocean. The idea is that if the AMOC gets closer to collapsing, deviations from the average temperature get more extreme and they show correlations between each other. This is a general behavior of systems near a critical point, which has also been observed, for example, in stock markets close to a crash or in Bose-Einstein condensates near the critical temperature, and so on. Fascinating stuff. In any case, the authors find that the AMOC is getting nearer to its critical point, and they estimate a collapse of the AMOC to occur around mid-century under the current scenario of future emissions. Another line of evidence is to check whether the conditions for a healthy AMOC are fulfilled. Spoiler alert, they aren't. The AMOC only works if the surface water in the north has a high enough salt content. If the salt content is too low, the water isn't heavy enough to sink down and close the AMOC circulation. But most of the ice in the Arctic and Greenland came from rain or snow. It's fresh water. Now that it's melting, it dilutes the salt content of the water. That makes the AMOC less efficient. The salt content of the water is measurable and we know it's dropping. A paper that appeared last year says that the climate models which the IPCC used for its risk assessment of the AMOC collapse don't take this into account properly. And finally, a recent reassessment of the AMOC collapse predictions that, I have to warn you, has not yet been peer-reviewed, found that, quote, the circulation collapses in all IPCC-class climate models in the high-emission scenarios and even in some moderate and low scenarios, despite the neglect of increasing Greenland meltwater influx. In most cases, the collapse is initiated by a breakdown of deep convection already early in this century. We conclude that a collapse of the AMOC can't be considered a low-probability event anymore. What'd happen if the AMOC shuts down? It'd move the flow of warm water and warm air further south. This'd mean more cold air in Middle and Northern Europe and more heat waves in Southern Europe. The full consequences would need decades to play out, but the models predict that temperatures in Northern Europe could drop as much as 10 degrees on average. Somewhat coincidentally, Germany is about in a range where the temperature drop from the AMOC collapse might just about average out with the expected 3 to 5 degree increase from climate change. However, this is just the average. We'd probably get more cold and heat extremes. It doesn't average out, just like if you get punched in the head from both sides at once, that doesn't average out to no punch. What all this means is that Europe is inching closer to a new ice age with every ton of carbon dioxide that we pump into the air. Yes, I'm taking some creative freedom with the word ice age, which is normally used to refer to a global event and not a regional one. But I think it's an apt description. And also, you see, it's always good to give other people an opportunity to complain. It keeps the blood flowing.
AMOC.
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 The Atlantic Meridional Overturning Circulation, or AMOC, is one of the most important climate systems on Earth and a key indicator of the health of our ocean. But is it in danger of decline? In this special mini-series from the creators of the National Oceanography Center's Into the Blue podcast, we speak to a range of experts to get to the bottom of the AMOC's potential decline and what we can do to stop it. Enjoy today's episode. Hello, I'm Dr. Zoe Jacobs, and in the first episode of our series all about the Atlantic Meridional Overturning Circulation, otherwise known as the AMOC, I'm joined by Ollie Tooth today to discuss what it is and why it matters to our climate. So, hi Ollie, thank you so much for being here today. So, can you start by telling us a bit about your career background? You're doing your PhD at the moment, right?
Yeah, so I'm in the last year of my PhD, not too long left. So I have come from an undergraduate in meteorology and oceanography. So I did that in UEA in Norwich, and then went from there to start my PhD in Oxford, where I work with Helen Johnson, and we study how the large-scale ocean works by following water parcels in ocean models. So we effectively study how and where they go, and also how they give up their heat to the atmosphere. Like that.
Cool. And do you work specifically on the AMOC?
Yeah, that's the main part that I work on. So I work on it in both the subtropical, so kind of the part of the Atlantic, which is between Florida and over to Africa, so that region there where we have an observing system, and also then much higher up, so that's typically where about our latitude, so where the UK is, and where we have an observing system there as well. So both of those parts that we look at in my research.
Nice. So I guess a good place to start really is probably by explaining to our listeners what exactly the AMOC is.
Yeah, so it's got quite a complicated thing to explain sometimes, but in essence, the really simple view of the AMOC is it's a large system of ocean currents which all work together to transport warm and relatively salty water from the subtropical regions all the way up to the high northern latitudes, so where we are and even higher, where it can then go and be cooled and freshened and then become really dense. At that point it sinks and then comes back and it effectively completes the loop. So you've got that full set of circulation like that. The AMOC, I had a moment then, a moment to pause. Another way, I suppose one way of framing it is to think of it a little bit like the central heating system, where you've got near the equator, it's a lot warmer, so it's a bit like a boiler, so we've got a real surplus of heat, and then the job of all the pipes, or in this case the ocean currents, is to redistribute that and take it further north. And so from our point of view, we benefit from that because that heat, once it comes further north, is released back to the atmosphere. And so we find that our climate here in Europe is typically somewhere between 3 and 7 degrees warmer on average as a result of the ocean moving all this heat further north. So it's really valuable to us.
Yeah, I see. That makes sense because I've heard it called like the ocean conveyor belt before, things like that.
Yeah, so the AMOC, when it's kind of become famous from the 90s, where there was a lot of work looking at past climate, so really even back to medieval times and periods like that, where we use sort of proxies of the climate system. You can't measure it exactly, so we use ways to indirectly get at the climate, where there was a lot of evidence to suggest that there were periods where the AMOC would completely shut off in the past, and that had massive climate effects, so plunging areas of Europe into what was called the Little Ice Age, so really drastic changes in temperature. And that's where this idea of a conveyor belt model came from, quite a simple idea. It's a little bit more complicated than that when we look at it now. And the last 30 years has really changed how we think about it, because actually, as I said at the start, there's lots of these currents that all together make up what we call the AMOC. And that means processes happening on tiny spatial scales all the way up to across the whole ocean basin are included in what we mean by AMOC as a concept.
Cool. And there is a lot of research that goes into it, right? And you kind of just touched a little bit on it there, but like, why do we care about it so much?
Yeah, so I suppose from the perspective of people in Europe, the selfish point of view is its role in the climate system and how much heat it brings north. That, in terms of, if you try to follow it through, so obviously from a general climate perspective, it does give us a warmer climate than what we'd have if there was not that heat coming northwards. But then it's also worth thinking about what it does in terms of the extremes as well. So if we think about that, the way we've discovered this is by actually shutting it off artificially in models. And when we turn off the AMOC in models, then we find that actually we get really strong seasonal extremes. So, for example, in summer months, we tend to find it becomes a lot drier in Europe, increasing risks of drought and areas like that. Whereas then, if you look in the winter months, what you see is that AMOC is really closely coupled to the storm track that in the UK we all kind of know and love because of it bringing these low pressure systems that are really
Do we love it?
Yeah, I mean, not at the moment. But so when we think about those kind of cold weather events, you're thinking of real rain, like strong rainfall. And in particular, if you shut off your AMOC, you see that those cold weather events and their impacts, particularly onto kind of infrastructure, the energy system and agriculture, they would all have a massive impact. So we do all kind of rely on it. And a lot of the time, I think we probably take it a bit for granted in our lives in Europe. It does have a bigger effect around the world as well. So obviously being very kind of European centric there, but if you think more broadly, there are parts of North Africa which are very much dependent on the AMOC sort of second hand because of the fact that it moderates how dry their climate is and therefore massive impacts on agriculture. And so going forward, that's a real risk factor, because if you have areas where you can't grow crops anymore, then you of course set up the possibility of migration, so environmental refugees. So it's not just a European kind of phenomenon in terms of how we benefit. It is much broader than that. There are lots of parts of the world more vulnerable than ourselves to climate change, which rely on what the AMOC does fundamentally.
So, I mean, it spans the whole Atlantic, right? But as you say, not just Atlantic countries that can get impacted. It can cause impacts globally.
100%. And there's also increasing evidence that it might also impact the Asian monsoon as well. So it's a kind of distant phenomenon where, of course, with a much larger population than what we have in Europe, impacts there are felt by much more people.
Definitely. Okay, so how do we go about measuring the AMOC? It sounds like quite a complicated task.
Yes, it is pretty difficult. And if you think back to that kind of analogy of this central heating system, that's trying to measure how effective your central heating system is at home is quite a difficult thing to do. The way you do it in the ocean is effectively we try and find a portion of the Atlantic where we can set up in an observing sense an array which will go all the way across the basin. So that way we put moorings which are effectively instruments which can tell us about the properties of the ocean and also the current speeds of the ocean across the section. And we need two things. We need to know how much water is actually flowing northward. So that is done with the currents themselves. We measure the current speeds. We also need to know the properties of that water as well. So if we want to understand how much heat the ocean is transporting, we also need to know about its temperature as well and also its salinity. So we measure those across a section like that, which goes up from one coast to the other. So the well-known one would be all the way from Florida to North Africa. And from that, then we basically take all of that data and we turn it into one number. And that number is telling us how much warm, light water is flowing northwards, which is balanced by that cold, dense water flowing south. And so it's effectively telling us what the rate of that cold, from warm to light to cold to dense is being transformed. That's what it's telling us as an overall measure.
Yeah, cool. So you've got that array, and that's called the rapid array, right?
Yeah, that's the rapid array, And there's quite a lot of others now as well. So the rapid array is quite famous. It's the first. So that was in place from 2004 and still giving us results now. That's where the amount of heat being transported north is its highest.
Yeah.
So that's part of the reason why it was put in place first. But now we have measurements that happen right up at kind of our latitude. So we have what's called the Oceanography Array, so overturning in the subpolar North Atlantic program. And that measures basically the amount of water that's being transformed between Canada across to Greenland, and then Greenland across to Scotland. So that gives us a real sense of what's happening at our latitudes. But there are also arrays all the way into the South Atlantic as well. So all of those are measuring the strength of this circulation at the same time, and will do so hopefully into the future.
Yeah, I hope
as well.
we can continue measuring, because it sounds really important. So we touched on how important the AMOC is for the climate. How does it translate to society? What kind of impacts can the AMOC have on us day to day?
Yeah, so this is where it becomes quite interesting to actually kind of explore, when I mentioned before about the climate system, and thinking about what the impacts mean in terms of, so two really good examples I think are agriculture and energy, particularly if we take a UK focus.
Yeah.
So we depend on our current climate now for obviously agriculture, and both in terms of production but also in terms of food security.
Yeah.
And some of the experiments I mentioned earlier where they've just turned off the AMOC, they've seen changes of up to 50% in terms of a reduction in the amount of primary production, how much food we can produce, and also up to 10% reduction in like the profitability in effect of agriculture. But then something that's kind of more thematic at the moment is about energy, because of obviously large global factors, but having periods where you've got really strong winter time events, like we've seen some in recent years, that's got a major impact in terms of where we get our energy from, demand, spikes in demand going forward. And so understanding how the AMOC will impact winter weather is really important in terms of energy infrastructure, and also obviously our reliance on UK energy versus overseas. So that both of those have an impact in terms of day to day, in terms of what we experience in our pocket fundamentally, in terms of what we spend money on. So the AMOC is fundamentally baked into how we operate in society.
Daily lives.
Yeah.
Cool. So one of the current big questions in ocean science is, will the AMOC collapse in the coming years? I was kind of wondering whether to bring this up or not, but there is a film that came out a while ago called The Day After Tomorrow.
Yeah.
And it's kind of the favourite scaremongering, what happens if this thing collapses? Now, I'm assuming that was a bit dramatic for what the reality would be.
Yeah, very dramatic, kind of very extreme examples, a little bit non-physical in places as well. But the idea of a collapse does come from this kind of the view I mentioned from the historical perspective, where we've seen the AMOC cause really abrupt climate change in the past. According to the latest reports, the IPCC that does work on this, that's the Intergovernmental Panel on Climate Change, they say that the risk of the AMOC collapsing by 2100 is very unlikely. However, there's always caveats with these things, which is these are fundamentally built on models, so computer models, and predicting the climate. And so there is some concern about how well we actually represent it, but at the moment it's very unlikely. With that said, we're sure that there will be a weakening. In the historical period, there has been a weakening. We know that with medium confidence. But looking ahead to 2050 and even beyond, it's very likely that there will then we will see a weakening going forward. And this is the challenge, I think, for AMOC science as a whole at the moment. Those estimates range quite a lot, from around 30 to about 45% weakening by 2100. So the weakening part's not necessarily a massive debate, but collapse and the major consequences is something that we're much, much less certain about and think is very unlikely overall.
Yeah, and this kind of complete shutdown, which you did mention earlier, we're talking like hundreds to thousands and probably millions of years ago about, for example, the Little Ice Age. Was that in the 1700s?
There's a 1300s and then 1500s around those times.
So hundreds of years ago, something like this did happen. But how quickly did it happen? Because we're talking about abrupt climate change, and like in the film, it suddenly is just like off, and that's obviously not going to happen. So how long would it take to completely shut down? Do we even know the answer to that?
So yeah, I would say we probably don't have a good sense of how long that would take. A lot of the processes, and we're saying a lot of the processes that bring about change to the AMOC are areas that are under real active research now. Particularly, so the big threat to the AMOC fundamentally is Arctic sea ice melt and also Greenland land melt of glaciers. And both of those things we know, because we have an understanding from kind of a historical period, will impact the way that this water is turned from that warm and saline to cold and fresh. But the exact way it does that is something that we're still actively exploring. And a lot of the time it's because the models that we use are constantly being improved and they're adding new processes in all the time to try and understand and improve the way we represent it. So that's one of the major reasons, I would say, that it's fairly unsure at the moment as to how it will
exactly.
pan out.
So I guess the reason that we're seeing a weakening is because there's a lot more meltwater coming off around the Arctic at the moment with climate change. So that is why we're worried.
Yeah, so the reason we're worried is, and that has been consistent even in those historical examples as well, the mechanism there is kind of semi-well understood, I'd say, in the sense of what we're talking about is a reduction in the amount of that warm saline water coming north because it's not being able to be transformed into the colder, dense water at these high northern latitudes. The question we have going forward, I think, to try and deal with is sort of whether the timescales over which that happens, and also where, if we have really large changes in fresh water in the Arctic, for example, how quickly do those changes travel down to the North Atlantic, and then what does it impact first in terms of, is it reducing the amount of warm salty water coming north, or is it changing that transformation as it goes from warm to cold as it loses its heat? Those bits are a little bit more unsure, and that's what a lot of people are spending a lot of time working on, because it's such a pressing issue.
Yeah, absolutely. And you mentioned, so on this, in the rapid array in particular, I remember in 2010 or 2011, everyone suddenly started getting worried because it took a massive kind of nosedive, didn't it? It weakened quite a lot and everyone was panicking. But it turned out, give it a few more years, it was maybe a bit of decadal variability. So how do we know, or how long are we going to have to measure for before we know if it's actually weakening, or if we're just looking at kind of decadal variation?
So that is a really, really important question. I think it comes down to almost the philosophy of studying the AMOC as well, which is to provide some context, that kind of circulation loop we mentioned, which is taking stuff from all the way through the Atlantic. We think that it takes a water parcel about 1,000 years to do that. So it's a very, very long time. And so for a long time with the conveyor belt view, we kind of thought about it as, if you make a change at the high northern latitudes, so put loads of fresh water in, then it would have a knock-on effect all the way down, like a conveyor belt would. But actually what we find when we observe the AMOC out in places like the Rapid in the subtropics is that the signal we get is really noisy. And it's because we're not just measuring what we call the AMOC, we're measuring lots of other things. And it's worth also at this point saying that a common misnomer, if you will, is that the AMOC and the Gulf Stream are the same thing. And so the Gulf Stream, it comes from, it's a wind-driven circulation. And so that will always be there, it's worth saying. But the Gulf Stream does then transport water, which as part of the AMOC as well. So this is really quite hard thing to pull apart. And so when we have these observing arrays, you're measuring multiple processes at once and collapsing them all into this number. So when we see a weakening, we've got some of the AMOC in there, but we've also got some other changes as well. And so one of the lessons from the RAPID program is just how much of this kind of short-term variability can make finding long-term signals really difficult. And that proves to still to be a problem. You need a longer record, effectively, to find those trends. Hence, there's an incentive to keep observing there in the future.
And let's hope.
Exactly. Let's hope we continue to do that.
Yeah, exactly. So if we do start seeing a weakening in the coming decades, what are the kind of impacts that we can expect to see?
Yeah, so if we take the UK as a good example of this, we tend to think about it in terms of, I mentioned before about an overall, we would expect a cooling, so we stop bringing that heat further north. So depending on kind of your estimates, it would be order of several degrees, which would be an overall cooling. But then there's some uncertainty as to whether that will mask the overall warming that we associate with climate change. In other words, it's taking a delayed amount of time for us to see that. When you get to specific seasons, that's when you start to see quite big changes in the sense of increased risk of drought. So drier summers is one thing that we have some confidence over. But then also one of the big impacts that the AMOC has as a knock-on is changing the storm track. So that is how storms arrive in the UK and across Northern Europe. And the sense is that it would likely become stormier as the AMOC weakens. So that means some of the wintertime impacts, that localised rainfall, particularly over on that west coast, which is obviously more exposed, we would expect then a lot more rainfall during those events. And so you can imagine already, just from recent experience, the knock-on effect of that in terms of flooding and how that could be an impact as well. So there's quite a lot of impacts from the AMOC that almost come to us, the secondary effects as it impacts the extremes of UK weather and also European weather as well.
Yeah, gosh, very integrated, like
it's hard to
process.
unpick them all. Yeah,
there's a lot going on.
So what are the most important scientific questions that you think need to be answered by the AMOC community over the next few decades?
Yeah, so I had a lot of thinking about this before coming in. And one of the main ones, I think, is whether or not asking the question of what drives the AMOC today is the same as what's going to change it in the future. They're quite distinctly different questions. And we kind of touched a little bit earlier on what could change it in the future. We have a pretty good sense that the impacts of fresh water are going to be really important. But we need to really focus in, I think, as a community on what those are and working out, because we've got lots of computer simulations now, how we can really kind of work out which bits we're certain about there and where there's real areas of uncertainty. Because it's worth saying that the AMOC is now, as we stand, one of the key areas of uncertainty in future climate prediction because it's just so poorly constrained, which has a knock-on impact to those effects. So that's one of the main things, is to try and kind of focus on what the process of change is. The other is then, the other things kind of fall from that, which is for observing, are we looking to observe the ocean in terms of where is it most likely to change? So where's your kind of fingerprint, if you will, of AMOC change? So we obviously have our array at 26.5 degrees north, which is the rapid array. But then is there anywhere else or any other methods we can use to try and pick up an early warning signal of AMOC change? There's a huge amount of effort going into that now and in the coming years. And then from the modelling point of view, I think you can take the same view, which is kind of what are the minimum processes that we need to represent really well, do a good job of including in our models in order for the AMOC and its prediction to improve, so we can reduce the uncertainty. I think coming decades, that will be a real drive for everyone, and knowing the community as well, that is a real focus going forward.
Yeah, I bet. Something I was wondering as well, there's a little, almost like a buzzword going around at the moment, tipping points. So if the AMOC does weaken substantially, possibly not collapse, obviously, but weaken substantially, is this something that can be reversible? Or once it's gone, no matter how much mitigation we are putting into place, it's not going to come back? Or will it come back?
Yeah, so the tipping points question is really interesting. So the idea of a tipping point being when basically a part of the climate system can change from one stable state to another, and it doesn't, that would be irreversible in that definition. And so when we think about shutdown, historically, we do know it's reversed. So we do know that those changes can be reversed on very long timescales. But in the present day context, we think it's very unlikely that it will collapse and so therefore change state dramatically. So at the moment, the sense of a strong weakening, when a lot of studies have been done, and they show that there is then a slow recovery in effect. But the key thing is we are in control of that future in the sense of we can mitigate that and reduce global carbon dioxide emissions, amongst others, and actually reduce risks of what is a plausible, albeit very unlikely outcome, which is a collapse of the AMOC. Much more likely is we would see this reduction going forward into the future.
Yeah, cool. Okay, so finally, and I'll be asking everyone in the series this question. So what needs to happen to protect the AMOC in the coming decades?
Yeah, so I suppose the straightforward answer is a little bit like what I just said, which is I think kind of the level of national level and governance is about really focusing on our impacts on the global climate as a whole, and obviously behaving more sustainably is clearly a really important part. But in terms of the community and how we communicate, I think that's another really important component of this, which is actually taking AMOC science from something done by oceanographers to a much more interdisciplinary approach. So we've talked a lot about how the physical climate impacts of the AMOC then translate into people's lives, agriculture and such. But actually more when looking into this, you find that there's actually not a lot of information about that. there's not many instances where we've gone from a future AMOC weakening at different levels and translated that into what the economics and what the social consequences are. So for me, the big kind of aim now is for the community to work with other scientists and in different specialisms to try and really communicate the value of the AMOC in a way that policymakers that are looking to produce a more sustainable, equitable world can actually understand and do something with beyond just the science element that we have today.
Yeah. Great. Well, thank you very much for joining us today.
Thank you so much for having me.
To find out more about NOC's research into the AMOC or to check out the other episodes from this mini-series, visit our website, noc.ac.uk. If you'd like to listen to more of our podcasts, both seasons of Into the Blue are available on our YouTube channel on all major podcast platforms. See you next time.
AMOC.
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 Yes, hello everyone on this exceptionally hot day in Vilnius this morning. I want to talk about one of the most ominous dangers of global warming, namely the danger of passing tipping points in the climate system, and in particular my research topic for more than 30 years, the tipping point of the so-called Atlantic overturning circulation. So what is the Atlantic overturning circulation, or meridional overturning circulation as it is called, in short AMOC? Meridional just means in north-south direction. It is a warm surface flow going along the entire length of the whole Atlantic, from the South Atlantic to the very North Atlantic, shown in red here. In the northern Atlantic, the water sinks down to 2,000, 3,000 meters depth, and then it returns as this cold deep current, the North Atlantic deep water, back to the south, shown in blue here. So you have warm waters moving north along the entire length of the Atlantic Ocean, sinking down, giving off its heat first to the atmosphere and returning then back south as a cold current. It works like a central heating system, and it has a massive influence on European climate, and not only European climate. So this is not the same as the Gulf Stream. It's often confused, but this flows along the Gulf Stream path of the North American coast. So in that sense, the Gulf Stream is a part of that larger scale overturning motion of the Atlantic Ocean. This last slide was a little bit simplified. Reality is more complex. Even this diagram is still simplified, but the deep water formation, as we call it, so the sinking down of the water to the depth of the ocean, because it gets very heavy, this water, happens first of all in the subpolar Gyre region, but a second big region is up in the Norwegian Sea. Now, the effect on climate is really large. This is what the world would look like compared to today's climate if you just switch off that AMOC. And you see the scale goes from 20 degrees Celsius colder to 20 degrees warmer. And you see especially the whole northern hemisphere would cool if you shut down the AMOC, and the whole southern hemisphere would warm. And off the Norwegian coast, annual average temperature there would cool by about 20 degrees Celsius. This is not just a theoretical idea, because we know there have been abrupt climate changes in Earth's history, most notably during the last ice age, and they are caused by abrupt changes in the AMOC. In this case, this diagram shows the so-called Dansgaard-Oeschger events. They are actually abrupt warming events that happened when this deep water formation flipped from being in just the subpolar gyre region in this state to going further north into the Nordic seas, and already this had a massive influence on temperatures over Greenland, shown in blue here. This is from a Greenland ice core. These Dansgaard-Oeschger events with the numbers, they are abrupt warming events of the order of 10 degrees within a decade or so, and then lasting for hundreds of years until the system flipped back down again. Likewise, there have been occasions when a lot of meltwater from the ice sheets went into the North Atlantic, iceberg armada slipping down of the ice sheets, so-called Heinrich events, which shut down the AMOC, which then had a massive cooling effect. So these instabilities in the AMOC have repeatedly happened in Earth history, and they had massive climate repercussions. So what is happening now as we are in a phase of extremely rapid global warming, now ongoing about 20 times faster than the end of the last ice age? No similar rapid global warming has been known in the Earth's history. I'm a paleoclimatologist, studied paleoclimate for over 30 years. And this is just the last 2,000 years. We see on the top the carbon dioxide increase, and on the bottom the temperature increase. We're now at about 1.2 degrees. And of course, this is not, we don't think because of this correlation that the CO2 causes the warming. We knew that beforehand. That was already known in the 19th century. The first person who quantified the coming global warming effect due to CO2 increase was the Swedish Nobel laureate Svante Arrhenius in 1896. So what is happening if you look at the map of this warming? That's what it looks like. The observed warming since the 19th century, the entire planet has warmed with one big exception, namely the northern Atlantic, exactly the region where the AMOC delivers its heat. And that has been predicted for a long time by climate models. Here's an example from the last IPCC report. This is now a scenario for the year 2100 for the temperature change, and you see again the whole world warming. This region in the northern Atlantic cooling in the forecast, and that is because the AMOC slows down in these IPCC future scenarios. Now, to study this in more detail, we use these climate models. This is what the sea surface temperature looks like in a global coupled climate model, ocean atmosphere model, the typical type of model being used for future projections. And you see nicely in dark red, that means warm water, the band of the Gulf Stream moving up the North American coast, separating from the coast at Cape Hatteras, that is this little corner here is Cape Hatteras, and then becoming unstable into these meanders. But generally, the heat gets transported further up and is given off to the atmosphere there. And if you use this model and ramp up the CO2 concentration in this model, then you can you get this sea surface temperature change in the model. Now, this has been normalized. That means it has been divided by the global mean sea surface temperature change. All you need to understand about that is that everything that is blue has warmed less than the global mean sea surface temperature or even cooled, and everything that is orange or red has warmed more than the global mean. And now you can see that cold blob in the northern Atlantic in the model simulation, but you can also see a very strong warming of the North American coast there, north of Cape Hatteras, where the Gulf Stream leaves the coast. Now, both these phenomena, both the cold blob and the warming of the American coast, is actually caused by a slowdown of the AMOC in that climate model simulation. And of course, in the climate model, we know this because we have the full information, unlike from the real world, where we don't actually have measurements of the AMOC going back for the last 100 years or so. So we don't have this information. I'll come to that. But in the model, we know everything that happens, and also we understand the physics, because when the AMOC slows down, it not only delivers less heat to the northern Atlantic. That explains the cold blob, of course, but it also makes the Gulf Stream shift closer to the shore along the American coast there, which leads to that strong warming up north, and to the south of it you can just recognize a blue bit where it's cool. So the Gulf Stream has shifted a bit north, and that's also a result of the AMOC slowing down. The physics of that has been understood for about 20 years now. Now this is what the observed sea surface temperature data look like when they are plotted in the same way as the model simulation. And I think you can see the same kind of pattern, only it's very fuzzy because we don't have sea surface temperature measurements since 1817 every year, everywhere. So there's an amount of space and time averaging involved in reconstructing this trend. But I think this fingerprint pattern of an AMOC slowdown, including the cold blob and the warm part at the American coast, is clearly visible. And this pattern corresponds to a slowing of the AMOC by about 15%. We can also look at this with the satellite data since the beginning of sea surface temperature satellite data sets. Now you get it in much higher resolution, of course, because it's satellite. And again, you see beautifully this fingerprint pattern, you see the cold blob, but now you can also see how there is this warmth along the American coast, and to the south of it there is a bit of blue, so the warm Gulf Stream has shifted indeed closer to the shore. So it's enlarged a little bit. So I'm talking about this warm streak here and this colder one. The whole current has shifted north and it has weakened, which leads to that cold blob. Similarly, the salt content of the ocean has decreased in that cold blob region, which is of course what you expect when the AMOC slows down, because the AMOC brings salty water from the subtropics up into the high latitudes. Subtropics, a net evaporation region, that's why the ocean is salty there. The high latitudes are net precipitation region, that's why the ocean is not so salty there. So we have a decrease in salt content in the cold blob region, and we have this increase in salt content here where the Gulf Stream has moved north. So that entirely fits this pattern as well. And the data actually show that as long as we have the data in the last 120 years, the salinity in this region is now the lowest that has ever been observed. Also, there are studies that directly look at the Florida current, which is a southern part of the Gulf Stream going up the coast of Florida, and that has actually weakened. Another study that came out last year shows robust weakening of the Gulf Stream itself during the past 4 decades. So this is all corroborating evidence for the fact that the AMOC has indeed been weakening in the last decades as a result of global warming. We can use sediment data and other types of paleoclimatic data to look at this phenomenon even further back in time. And we recently published a study a few years ago compiling evidence from other studies from paleoclimatologists that work with these deep sea sediments and so on. The studies are listed there, reconstructing the strength of the AMOC for the last 1,000 years and more, and they all agree. They all show a pretty stable AMOC for the last 1,000 years, but then in the last 100 years or a bit more, you see this very strong decline, and our conclusion in this study was that the AMOC is now weaker than any time in at least a millennium. Now, what consequences does this weakening of the AMOC have for our climate? Just one slide on this, maybe a bit surprising to you. It actually leads to stronger heat waves in summer in Europe. Why is that? A study showed that in 2016. It's because that cold blob likes to have a low pressure area above it, and the low pressure, you know, the wind goes counterclockwise around that low pressure, as shown by the red arrow there. And so we get warm air coming from the southwest into Europe, enhancing the probability of heat waves. And that has been shown again 2 years ago by a study from my department at the Potsdam Institute, showing that Europe indeed is a hotspot of heat waves where they are increasing 4 times faster than on average at similar latitudes. And it's shown in this map here, but also in this probability distribution where this kind of, it's like a Gaussian normal distribution of heat, and it shifts to the right with global warming, of course, towards warmer temperatures. And the blue one shows how typical mid-latitudes on average have shifted the heat wave intensity to the right. And the red one for Europe, it has shifted much further to the right. So just showing that indeed heat wave intensity in Europe is increasing much faster than elsewhere in comparable latitudes. Okay, now I promised to talk about a tipping point. So that's our next part. In the first part, we have seen the AMOC is already weakening, and the second question is, what about this tipping point? Now, a tipping point can be explained quite easily. It's, imagine a ball sitting in this bowl-shaped thing here, and if this person pushes it a little bit, it will roll back to its equilibrium, because that is a stable equilibrium, except if the person pushes that ball beyond that apex point shown by the arrow there. If it goes over that hump, from then on, it will continue its movement without further pushing, just by its own internal dynamics. And that is the definition of a tipping point, also by the Intergovernmental Panel on Climate Change, IPCC. And you see from this simple example, you don't need rocket science for that. It's something very common in physics. You can, if you're a school student wobbling around on your chair, you can do it so far, and from a certain point on, your chair will just fall over. There's another example of a tipping point, or push your coffee cup to the edge of your desk. If you push it too far, yeah, you get the idea. And this is exactly how tipping points in physics generally, and also in the climate system, happen. The first person who prominently warned about this for global warming was the famous American oceanographer Wally Broker. And he wrote in the top science journal Nature in 1987 about these unpleasant surprises in the greenhouse. And that is an article exactly about the risk of abrupt ocean circulation change as a result of global warming. And he put it quite drastically. We play Russian roulette with climate, and no one knows what lies in the active chamber of the gun. More modern view of this, now we have a big 500-page report. Last year, 200 scientists from over 90 institutes from 26 countries wrote this massive report and concluded that harmful tipping points in the natural world pose some of the gravest threats faced by humanity. Their triggering will severely damage our planet's life support system and threaten the stability of our societies. That is really what we're talking about here. The IPCC has made similar statements saying that risks associated with large-scale singular events or tipping points, such as ice sheet instability, it's a classic tipping point, ecosystem loss from tropical forests, for example, transition to high risk from moderate to high between 1.5 and 2.5 degrees of global warming. So that is here really giving a range where this is really becoming a high-risk issue. And it is, once we go above the 1.5 degree, this is becoming real high risk. And this is one of the reasons why in the Paris Agreement, all countries committed to efforts of limiting global warming to 1.5 degrees. So for the AMOC, let me quickly explain how this tipping point works. This is from a paper in 1961. Another famous oceanographer from the United States, Henry Stommel, described the problem of the tipping point for the Atlantic overturning circulation based on a very simple model. And the equilibrium states for the AMOC, that's what on the vertical axis, the strength of the AMOC, are shown in the green lines, as they depend on the amount of fresh water going into the North Atlantic. Why fresh water? Because fresh water dilutes the salt content, and less salty water is less dense. The density, especially for the cold waters, depends mainly on the salt content. And so if you add too much fresh water, the surface waters get so light that they can't sink down anymore. And this sinking down motions of heavy water is what drives this whole overturning. And so when you start from an equilibrium, maybe round about here, and you add more fresh water, say from more rainfall with global warming, more ice melt from the Greenland ice sheet, then you move on towards the right here, but you come to this what is called a bifurcation in the language of physics, where this curve turns back on itself, and there is no more stable state with an AMOC. It has to break down from that point. Why does it look like this? It's very easy to explain. It's a self-sustaining feedback. The water sinks down because it's salty, but it is salty because we have the AMOC bringing salty water from the subtropics. And so if you just have a simple model with two equations, the flow is proportional to the density difference, and the density depends on the flow, you get a quadratic solution. That's what this is. It's a parabola here lying on the side. That's a quadratic solution. And it basically shows why there is this bifurcation point, which is the tipping point, of course. And of course, this is an equilibrium state, the equilibrium states, but with global warming, of course, we are moving away from equilibrium, and we're weakening the AMOC, so we're more on something like this blue trajectory now, where this actually, when it crosses this dashed line, it will cross the tipping point and will die, basically. It will break down. Now you can say, okay, this is a very simple model, two equations, etc. But already in the 1990s, I repeated this, I tried this with a fully fledged three-dimensional ocean circulation model, global model, and there you can't calculate an equilibrium because it takes thousands of years of model simulation to really equilibrate the system, but you can gradually ramp up the amount of fresh water. That's what's done in the orange line there, until you fall off the cliff there. And if you do the same ramping up experiment in Stommel's box model here, you get the black line. If you do it in a fully three-dimensional global ocean circulation, you get the orange line, and you see they're exactly on top of each other. So the very simple box model by Stommel is kind of one-to-one confirmed by fully 3D ocean circulation model. And it has been tried with a number of models now, and you always get this kind of result. So this is really confirmed that this tipping point really exists. Now, the big question, of course, is how far away are we from this tipping point? And this is where there's a big uncertainty. And there are many reasons why models probably underestimate this problem. For example, if you look at what do global warming simulations show up to the present, if you run a global climate model with the CO2 increase and other greenhouse gases, etc., that we have seen up to now, you get this right-hand side picture from the IPCC report. This is what the observations show. So the models, they only predict this slowing of the AMOC for the future, as I showed you in an earlier IPCC diagram, but not yet, but we're already seeing it now. So that's one reason to think the models underestimate this problem.
Delicate balance of salt and fresh water.
We all know that.
Yes, but no one has taken into account how much fresh water has been dumped into the ocean because of melting polar ice. I think we've hit a critical desalination point.
So I don't know who of you has seen this movie from 2004. It is exactly about this ocean circulation passing this tipping point. And so that's what he calls a critical desalinization point. It's because of the fresh water. And he says in this little clip, no one has taken account of the melting of all the polar ice, and that is still true in modern climate models because most of them don't fully include the meltwater coming from increasingly rapidly melting Greenland ice sheet. It's just most of these climate models don't have an interactive Greenland ice sheet included yet. And that's another reason why they probably underestimate in the future scenarios the risk of passing that tipping point. Then also the tipping point, of course, depends on a very subtle balance of salinity in the whole Atlantic Ocean, in 3D, down to the depth, etc. And this is very difficult to get right in the models because it depends on evaporation minus precipitation. You need to really accurately simulate the precipitation, all the clouds, etc. over the Atlantic, where we have very scarce observational data about rainfall amounts for the first place. And also, clouds are notoriously very difficult to get right in climate models. And so, typically, climate models are very biased in the salinity distribution. And here's one study that has corrected that bias. And before they corrected the bias for the future, they get the AMOC weakening, that's the blue curve, but not going over the tipping point. Then they adjusted the salinities in the South Atlantic, actually, to get a more realistic picture, and then they got the orange response to a standard CO2 increase scenario. So that model shows if you improve the salinity distribution in the Atlantic, then the AMOC becomes more unstable and in a regular global warming simulation already passes the tipping point and breaks down. Now, another way to try and find out where the tipping point is comes from nonlinear physics, not at all from climate science, and is the so-called early warning signals or critical slowing down. So it's if you have the ball in that ball-shaped thing again as an analogy, and there is noise, then it will wiggle around the whole time to some extent. Now you change the climate, so you change that background, that black curve. It is still going to wiggle around here, but the side is more flat now, so it will take longer to come back to its equilibrium, and that's what's called critical slowing down. And you can observe the random variability of the system and look for signs of that slowing down or increased autocorrelation. They're all signs of approaching a tipping point. And that has been done in a number of studies, an important one by Niklas Börs from the Potsdam Institute. He looked at 8 different data sets for the AMOC, reconstructed based on temperature patterns, etc., because we don't have direct measurements going back very far. And to cut a long story short, where these dashed trend lines hit the top of the graph here, the 0 line, that's where the tipping point is in this early warning signal analysis. And this is quite scary because, you know, in the 2000s, early 2000s, 3 of them with a salt content, 2 further already suggest that's where the tipping point should be. So it might be actually very close. We could have even already passed it without noticing because nothing drastic happens at that point, except that from now on there will be an unstoppable decline of the AMOC, and we will know that in a few decades whether this is really happening. That was the conclusion from that study. Here's one that used data going back more than 1,000 years, a lot of sediment data from all these points around the northern hemisphere, because you can see that Atlantic variability in the whole temperature data history of the northern hemisphere. And they find at the end here this critical slowing down, and that study concluded that the AMV, which means Atlantic multidecadal variability, but it actually refers to the AMOC, may now be approaching a tipping point after which the Atlantic current system might undergo a critical transition. And there have been more recent studies, there have been newspaper reports like this one from the Washington Post. Here's another one from the New York Times from a couple of years ago. And new studies coming out. Last year, you might have seen the headlines about this Danish study. And quite recently, there was a study from Dutch colleagues from Utrecht, who are, I think, the leading group in this topic now. And actually, on Monday, I go to a workshop for a 3-day workshop on this AMOC tipping point in Utrecht with this group of scientists. Yeah, it's really not looking good. It looks like so far greatly underrated danger. And just to remind you what the consequences would be, this is now for the February temperatures in the model of that Dutch group. When you go over that tipping point in the following 100 years, this dark blue areas now, they cool actually by 40 degrees Celsius over that 100-year time span after the tipping point has crossed. So we're talking about like 4 degrees per decade. It's shocking. I mean, now we've had 1.2 degrees of warming over a 100-year time span. And now if you get several degrees of cooling per decade, this is going to be detrimental. Now, this is only the AMOC change without global warming considered with it, but there are also simulations that look at a 2 times CO2 scenario, so doubling of CO2 in the atmosphere, and the AMOC has collapsed. Then it looks like this. In the top picture is a temperature change in the annual mean, so you have the entire globe got a lot warmer from the 2 times CO2. And except for the North Atlantic region, including Great Britain, Scandinavia, that have cooled massively. And sometimes I get asked by German journalists, oh, well, doesn't that nicely compensate global warming? If the AMOC shuts down, we get the cooling and the effects compensate. Now, you might say where it's white, actually, yeah, in annual mean, they might just about balance. But look at how the temperature gradient across Europe changes there. Of course, the weather, sometimes you get cold air coming from the north, sometimes you get hot air from the south, and this is going to get much, much more variable if you have such an increased temperature gradient. Also remember that winds are driven by these temperature gradients. So this looks like a crazy stormy climate to me with absolutely unprecedented weather extremes all across Europe. But let's go back one here to look at the bottom panel. This is a change in precipitation patterns. And here you see a phenomenon that the tropical rainfall belts have shifted south. So where it's purple now, it's getting a lot drier, and where it's green, it's getting wetter. And that is because the northern hemisphere gets cooler and the southern warmer, and the tropical rainfall belt is where it's warmest, and the air rises and therefore rains down. And in our current climate, the northern hemisphere is 1 or 2 degrees warmer than the southern hemisphere overall because of the AMOC transporting so much heat from the southern hemisphere into the northern hemisphere. So once you turn off the AMOC, both hemispheres will have approximately the same temperature, and the tropical rainfall belts, which are now north of the equator, will move south. And that means the tropical rainfall is not anymore where the rainforests are. That'll be a big problem. And regions that are not used to big, massive tropical rainfall amounts are then getting them. So this will be a massive problem in the tropics as well, not just in Europe. So if you want to read more about this thing, I just published a summary of 30 years of my collected research and wisdom on this topic. Open access, understandable, and fully peer-reviewed. So in this article, you can download it from the journal Oceanography. You can read all about it. My summary conclusion here, the AMOC is weakening. I'm convinced that the evidence is overwhelming for that. We also are certain that it has a tipping point, but the big uncertainty is how close the tipping point is. But recent studies really point to a risk being much larger than we thought, than even I thought until 5 years ago or so. And therefore, we must apply the precautionary principle. This is a disaster we need to avoid at all costs. And that is something that also the IPCC agrees with what the IPCC is saying about global warming in general. There is a rapidly closing window of opportunity to secure a livable and sustainable future for all. We're sure about this. And the choices and actions implemented in this decade will have impacts now and for thousands of years to come. That's because CO2 stays in the atmosphere actually for more than 100,000 years, unless we actively pull it out again, which is hugely expensive. And so what we do this decade decides our climate fate for thousands of years, even without tipping points. Of course, when the AMOC is tipped, that's it, it'll stay off for probably 1,000 years at least. That's why these European elections coming up, of course, are extremely important. It's all about whether the European Green Deal will survive or whether it will be watered down massively. That is really a threat if the majority in the European Parliament is changing after this election. So that's what I wanted to tell you. If you want to read more, I've written a couple of books. And thank you very much for listening. Thanks.
AMOC.
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 Hello, I'm Paul Beckwith. In recent videos, I've talked a fair amount about the AMOC, or the Atlantic Meridional Overturning Circulation, because it's such a vital system on our planet. It's a vital part of the climate system, the overall system, how heat moves from the equator to the poles in the atmospheric circulation patterns, also in the ocean circulation patterns. And, you know, we've had an AMOC that's slowing down, and we're approaching a possible tipping point where it abruptly shuts off. And there's obvious effects if that happens, including the cooling of Western Europe and the cooling of the whole North Atlantic, Eastern Canada, and a shift in monsoons, a shift in the intertropical convergence zone, changes in the Amazon rainforest, perhaps. There's a whole cascading sequence of events that can happen. And just yesterday, a professor at the University of Ottawa, who I don't know, put out a thread of tweets talking about his research recently on the AMOC, asking a lot of questions. So I think it's a useful exercise for me to go through that, because as much as I've talked about it in previous videos, there's additional information on this thread. So let's get right into it, shall we? It's in 2 days I leave on my travels to Baku. Please consider going to my website, paulbeckwith.net, and donating to PayPal to support my research and videos. Or you can directly go to the GoFundMe. I'll put a link in the description to consider offsetting my direct costs of air flight and accommodation and food, etc. There's a GoFundMe which my friend Heidi set up for me and organized it for me to go to the UN climate conference. So just going in a couple of days, lots of stuff to do before I leave. Okay, so this is a graphic showing a highly simplified schematic of the Atlantic Meridional Overturning Circulation. Warm water crossing here, coming up, and this is basically the Gulf Stream coming across, bringing heat across the Atlantic over to Europe. So this provides a lot of the heat, right? England, a lot of places in Europe at fairly high latitudes. You can compare the latitudes over to Canada, northern Canada, and they're a lot warmer in spite of their high latitudes, because of this tremendous heat being carried in the ocean currents. And then the water cools down and gets saltier and descends to the bottom of the abyss and traces back, completing, this branch of the North Atlantic, South Atlantic branch of the overall ocean circulation. This is the observational sea surface trend from 1993 to 2021 in degrees Celsius. So we can see the water's a lot warmer here off the U.S. coast, and up here in the off Scandinavia, etc., is much warmer. There's a cold spot here. This is a so-called cold blob or global warming hole, and this is very concerning because we would expect this to happen if the AMOC is slowing. And in fact, the AMOC is slowing, and the concern is it will just reach a tipping point. So this is data from the Copernicus Climate Change Service, and you can go to their website, climate.copernicus.eu, to get more information. Okay, so that was the second tweet. Let's start at the beginning. This is Ryan Katz-Rosine, who's a professor at U Ottawa studying contentious climate politics. And I don't know him. I've never met him. I'll have to invite him to come on to the Climate Emergency Forum to have a whole session about these findings from AMOC. So here's what he was asking just yesterday. I've been wondering a bunch of things about a potential AMOC collapse. When will it tip? What are the most likely effects? Can we stop it? So he looked for answers in the many scientific papers published on this and generated this plain language thread with his findings. So this is a list of the papers that and this is in alphabetical order. He's done it alphabetical order. Probably would have been better to do it by date, but there's a lot of 2024 papers. It goes back to about there's a 2014 paper here. This is the furthest back. Okay, so some of these papers you'll recognize because I've done entire videos on them. Weaker Atlantic overturning circulation will increase the vulnerability of the northern Amazon rainforest, because if it shifts the rain belt southward, right, then the northern Amazon rainforest will become savanna and grasslands, and the carbon sink will fail. So this would have a huge impact on the planet if in fact the northern Amazon collapsed. Is the AMOC shutting down? Paper from October 24th, 2024. Further climate change shaped by intermodal differences in AMOC. Observation-based early warning signals for a collapse. These papers are from 2021. Early warning signals of AMOC collapse in fully coupled climate models. That's a recent paper. From August 12th, observed fingerprint of a weakening AMOC, 2018 paper, simulated tipping by internal climate variability with a rare event algorithm. So they're trying to model, is this thing going to collapse? And if so, how quickly? Warning of a forthcoming collapse. I think this paper, 2023, they were putting dates on a collapse between 2025 and 2095 with certain probabilities. Warning of a forthcoming collapse. So there's more and more these are peer-reviewed scientific papers. Arctic freshwater outflow suppress Nordic seas overturning and oceanic heat transport. I think I covered that paper in a video. It's repeated here. It's a duplicate. AMOC circulation, observed transport and variability. Natural variability has dominated it. So it is very variable. It has these large swings, but it's important to try to find a trend. And when you get large swings in a system, increased variability, the system could be losing flexibility and resilience and be getting more brittle, if you like, as you approach a tipping point collapse. I think that's what could be happening. AMOC decline and recovery in a warmer climate. Interbasin and interhemispheric impacts of a collapsed AMOC from 2022. A couple papers by Rahmstorf. Is the AMOC approaching a tipping point? And then he did an open letter by climate scientists to the Nordic Council of Ministers just recently, and I talked about that in a video. Ongoing AMOC and related sea level and temperature change after achieving Paris targets, 2020 paper. Probability estimates of a 21st century AMOC collapse and physics-based early warning signals. Do we have early warning signals to know that the AMOC is about to collapse? That's a very important paper. Okay, so you can Google any of these titles and find these papers. Some will be behind paywalls, other ones won't be. You'll be able to access the PDF. So it's a good sort of overall summary for you. Now, WTF is the AMOC. It's the Atlantic Meridional Overturning Circulation, which is a fancy name for an important ocean current that it serves as a heat pump for Earth. It brings warm surface water from the tropics northward. Okay, that's the red line. Releases its heat, sinking, and then it brings deeper cold water back south. That's the blue node. Okay, so that's basically what the AMOC is. And how much is the AMOC weakening? So numerous studies show that the AMOC is indeed weakening substantially, more than even the latest climate models expected, and that it's at its weakest state in the last 1,600 years. So here's where we are. This was a paper, I think, it came out in 2021. Okay, this is the AMOC strength for the past 1,600 years, reconstructed from paleoclimate data sets. So this is a temperature anomaly in the cold blob region from Caesar et al., a paper in 2018, and there's other data that scaled to it. So this is going back 1,600 years from just about 2000. You can see how much the AMOC has weakened. The AMOC, weaker AMOC, the temperature anomaly in the cold blob gets lower, colder and colder and colder in the cold blob, indicating an AMOC weakening or slowing down. So there's many different data sets, and they get sea surface temperatures, there's proxies on the land, there's subsurface temperatures measured, deep sea coral data, silting data, measurements. This is a rapid array of sensors across the Atlantic, and benthic plankton, so plankton that are in the sediments in cores. Okay, so there's all of these different data sets, and they're all showing the same sort of thing. They're showing this cold blob developing here, and getting stronger, and indicating the AMOC is weakening. Okay, temperatures would be higher for stronger AMOC, weaker for colder temperatures. Okay, so the AMOC is doing weird things for sure. Now, what's the difference between the AMOC weakening and the AMOC collapsing? So Stefan Rahmstorf is one of the world's leading experts on the AMOC. He has an example. If you're leaning, so it's like a tipping point. Okay, I talk about being in a canoe and tipping. You think about leaning back on your chair. So you can lean back and control how far you lean with your legs up to a certain point. Right, up to a certain tipping point. Once you pass that threshold, the chair falls backwards. There's nothing you can do about it, right? You're flailing, you end up on the floor. So the AMOC is bimodal in this way. It's either on, with like the upright chair, and it's flowing, or it's off, like the chair tipped over and now you're on the floor. Models of the AMOC tipping from the past show that after it tips, there's a 100-year free fall in the strength of the current. This 100-year period is like the chair falling backwards. Okay, so there's a graph here. Don't be confused by the dates. It's based on a model run showing how many years into the model a collapse occurs based on the model's assumption. So it's not showing an actual year, but it's just showing the features, the shape of the current flow. So you can see how eerily the model reflects early phases in the observed weakening of the AMOC over the last 1,600 years. Okay, so we just showed you this plot here, and now the model is showing this here This is AMOC strength at 26 degrees north. It's actually 26.5 degrees north. There's an array of ocean buoys across the Atlantic. And you can see that, you know, when the AMOC strength weakens enough, this is volume transport in Sverdrup. So Sverdrup is 1 times 10 to the 6 meters cubed per second, something like that. It's a way to measure ocean currents, river flows, etc. So anyway, you can see a weakening of the volume transport past 26 degrees north, and then suddenly, boom, it tips. It abruptly slows to 0, okay, at 26 north. So you can see that happening, basically. Okay, so you go, it's like your chair. Your chair's upright, suddenly your chair's on the floor. There's a tipping point that we've passed. Very highly nonlinear behavior. Now, what are the main effects? There's a lot of uncertainty. I don't know why it flips like that. What are the main effects? There's a lot of uncertainty about how much of the following would occur, especially because the AMOC is just one force. There's also competing and interconnected changes in the Earth's climate system. But generally speaking, the main expected impacts of an AMOC collapse are we'd get a significant expansion of the cold blob area size into northern Europe. Eventually, some areas like Scotland, England, Scandinavian countries would become much colder than present. In some of these places, it will eventually be too cold for agricultural production in these places, Scotland and the Scandinavian countries. We're talking about maybe drops of up to, 5, 6, 7, 8 degrees Celsius in the UK, and maybe even 16 Celsius drops in Scandinavian countries. These are mean annual yearly temperatures. It's going to get cold in those regions. There'll be a change in the thermal equator, if you like, because it's much colder in the North Atlantic. There will become a southbound shift in the tropical rain belts, the intertropical convergence zone. This would change the aridity precipitation sign in the northern and southern tropics, where the currently much wetter tropics would get much, much drier, and the currently drier southern tropics would become much, much wetter. The ITCZ would shift southwards. This is again catastrophic for agricultural production, since we're talking about eventually the potential conversion of areas that are naturally tropical rainforests now will be converted into dry savannas, and areas that are right now dry savannas further south will become tropical rainforests. Not good, right? Not good for growing crops, especially during that shift. Note, this figure shows temperature and precipitation 300 years into a model of AMOC collapse and a doubling of atmospheric CO2. It's not quite a clear representation of what things would look like this century, even if the AMOC starts tipping. But it's roughly a 100-year collapse phase, the AMOC collapse. So this shows you, and I showed you this figure in a previous video, where you would see a much, much colder region in the North Atlantic, Northern Europe, UK, Scandinavia, Eastern Canada, and Western Europe, very, very cold areas, and a shift downward of the rain belt. So this is where the rain's presently falling, the ITCZ, and that would shift further south. So this would become much, much drier. This would become much, much wetter in those regions. Okay, so I've shown you that previously. Now, sea level changes. Let's do our shifting again. Okay, sea level changes. A complete collapse of the AMOC would have major consequences on sea level changes. It would contribute to a lowering of sea level in some places, partly counteracting expected continued sea level rise from melting ice sheets and thermal expansion, and it would cause sea level to rise further in additional places, in addition to melting ice sheets and thermal expansion. One of the worst hit areas for sea level rise is the North Atlantic coastline. After a century post-collapse, it's expected to contribute an additional 1 meter of sea level rise there. Okay, so above and beyond normal sea level rise, a collapsing AMOC would contribute an additional 1 meter of sea level rise to New York City and all the way up the coast here of the U.S. into the Maritimes, Newfoundland. The biggest sea level rise would be actually out in this region here, and the sea level would correspondingly also up here and here, and this would undercut, the sea level rise here would likely destabilize Greenland even more within its melting, and then you'd get lower sea level rise in some regions here. Okay, so it would monkey with the sea level rise. There'd be those effects. And then after that post, dang, he ran out of time. He had to go teach. Okay, so eventually we'll get to the question of how likely is it that AMOC will reach a tipping point in the next few decades? Just warning you, the answer is not a happy one. Okay, so he's back. He's back after his teaching. Hope his teaching went well. Let's do this. Okay, so continued the main effects of AMOC collapse after temperature changes, precipitation changes, I've shown you those, and sea level changes. We would have changes to the ocean ecosystems. So an AMOC shutdown would reduce oxygen supply to the deep ocean, right? Because we wouldn't have that warm water crossing and then descending. So the deep ocean would not get oxygen, and it also so it doesn't get oxygen and the nutrients also. The nutrient supply is changing, right? The whole vertical distribution of the ocean changes, and that's bad for ocean ecosystems. So we would get disrupted oxygen supply going to the deep ocean, and disruption of the existing patterns of ocean nutrient cycling. Similarly, a shutdown would disrupt the temperature and salinity balance of the Atlantic Ocean. These changes could disrupt ecosystem productivity and habitability for various marine species and work their way up the food chain. One study looked at the last interglacial period in the Nordic seas, about 128,000 to 117,000 years before present, when it was very warm globally, thus potentially triggering a natural sort of AMOC collapse. And there was a major transformation seen in the ocean ecosystems of various species as a result of the changing temperature, salinity, and oxygen levels, which is what this figure shows. Okay, so I think I also showed you this figure. It shows you that I showed you this paper in a previous video just within the last few weeks, I believe. And it shows sampling of sediments in different regions, and it looks at the oxygen changes. It looks at the changes in some of the plankton in the sediments, various types, and these are solar insolation changes at those periods of the last interglacial, and there was a disruption of ecosystems as shown in the ocean sediments in this region. Okay, so definite ecosystem changes. Another effect is that there's teleconnections to other global climate impacts and tipping points. This is the part that gives me goosebumps, right? We're talking about cascading tipping points here. So what happens in the North Atlantic doesn't just stay in the North Atlantic. Gee, where have I heard that phrase before? That's my phrase, and it was about the Arctic. But anyway, if the main heat circulation pump in the ocean shuts down, it could, what could it do? It could potentially serve as a catalyst for other Earth system feedbacks and potentially kickstart other tipping points. We know, for instance, that due to a shifting of the tropical rain belt, the Asian and African monsoons would be altered. We'd get a southward shift of rain in the Americas, and that could result in a dieback of the Amazon, a global tipping point linked to a major reduction in Earth's carbon sink. An AMOC collapse is also expected to strengthen the Pacific trade winds and the Walker circulation, right, which is an atmospheric airflow loop, like so, and that would alter the ENSO, the El Nino La Nina cycle. The complete ENSO cycle could be altered by this. Finally, a collapse of the AMOC could lead to modest warming around Antarctica, which could exacerbate ice sheet loss, further contributing to global sea level rise. Well, guess what's happening around Antarctica since about 2015, right? We've had record loss of sea ice, Antarctica sea ice, and it caught people completely by surprise because it had been increasing about 1.5% per decade up until that point, and then it just reversed. So we're actually seeing modest warming around Antarctica and collapse of ice sheet, or the sea ice anyway, and that an acceleration of ice sheet loss, which does contribute to global sea level rise. Okay, there's a lot of uncertainty with all of these risks. So this just shows you this is the Walker circulation, right? It's coming this way at high altitudes. On the surface, it's coming this way. It causes the trade winds. So if this is stronger, the trade winds intensify. It keeps more hot water over in this region. And it affects weather pattern. It ties into global weather patterns and changes where the monsoons are, and has huge effects on which parts of the planet, the distribution of warming, the distribution of the sinks and sources. Some sinks are failing, the Amazon rainforest, right, shift, right? So there's all of these different factors that can occur. Sea ice extend, AMOC on, AMOC off, right? You can look in the details of this plot. There's loads of stuff in here about showing the atmospheric circulation and the ocean circulation and different temperatures and anomalies. So all of these things can happen, but there's a lot of uncertainty about the risks. So here's a question, one of the key questions. How soon could this thing reach a tipping point? The latest IPCC report, AR6, published in 2023, stated that there was medium confidence that the AMOC would not collapse abruptly before the end of this century. That doesn't give me a whole lot of confidence. A number of more recent studies have sounded the alarm that even the IPCC report underestimates the risk of a potential AMOC collapse this century. A paper published last year estimates collapse around the middle of this century, or sometime between 2025 and 2095, with a 95% confidence interval. Well, 2025 is next year. Another study that's currently under peer review gives a more precise range of between 2037 and 2064, with a 10 to 90% confidence interval, and notes that the mean estimate for AMOC collapse is the year 2050. Well, that's 26 years from now. The preprint, right, it's not peer-reviewed yet. It's a preprint. It's being peer-reviewed as we speak. It says the AMOC is on a tipping course, and there's a 59% chance, plus or minus 17%, that the AMOC collapses before 2050. And I did a separate video on this preprint. This suggests that a tipping point may actually have occurred decades ago. Could have already passed it. We're just seeing changes in the AMOC now, right? The tipping, it's not like it takes a while for your chair to tip over. This is a climate system. Studies note that a change point linked to salinity changes likely was reached back around 1970 rather. And then in this recent open letter to the Nordic Council of Ministers, scientists noted there's a possibility AMOC collapse is triggered this century, but only fully plays out in the next. It's way too close for comfort. And again, here's the AMOC strength at 34 degrees south. This is the volume transport in sphere drops, so it's meters cubed per second, million meters cubed per second. I think all the rivers of the world, if you add up the flows, it's about a sphere drop, one sphere drop, something like that, or maybe a couple sphere drops. But anyway, this is a huge change. The ocean currents are massive volume flow rate. And this shows you some of the forcings, freshwater transport in sphere drops, different forcings and so on from the model. So basically, it could happen any time. shamelessly plugging in our work on the potential collapse of the AMOC on species distributions. So there's a paper here which looks at animal and plant diversity and how that could change in different places with an AMOC collapse. I'm not familiar with that work. I may have to do a separate video on it. Okay, so that's basically the situation. Okay, so, you know, it's a thread. Maybe things will be added to it. There's still a lot of things that we don't know about the AMOC, but I think the thread actually puts a lot of things nicely in context. It gives the main key references over the last few years, and, you know, goes to, you know, a long way to sort of making us think about these questions. When will it tip? What are the most likely effects? Can we stop it? Right? So that's the whole point of this video. So thank you for listening. Again, I'm leaving in just a couple of days for Baku, Azerbaijan, to COP29. So please consider donating to my PayPal to support my research and videos, or more specifically to my GoFundMe to offset directly expenses, out-of-pocket expenses that I'm paying in order to go and attend the conference. And I'll be filming many videos, many interviews with people sort of ongoing over the next few weeks as I'm at the conference. The conference runs from November 11th, which is a Monday, to the Friday, November 22nd, and I fly back on the 23rd, and I think there's, you know, it runs through the weekend in the middle, and I think there's one rest day or something. But anyway, you'll be getting lots of updates, you know, maybe a travel log. I'm bringing my laptop. I'm bringing my my new iPhone. And yeah, there's lots of things in the works to you know, interview people, try to make a difference. Yeah, I'll keep you in the loop on a day-to-day basis. That's my plan for the conference. So thanks again for watching, and bye for now.
AMOC.
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 The Atlantic Meridional Overturning Circulation, or AMOC, is one of the most important climate systems on Earth and a key indicator of the health of our ocean. But is it in danger of decline? In this special mini-series from the creators of the National Oceanography Center's Into the Blue podcast, we speak to a range of experts to get to the bottom of the AMOC's potential decline and what we can do to stop it. Enjoy today's episode. Hello, I'm Dr. Zoe Jacobs, and this is the second episode in our series about the Atlantic Meridional Overturning Circulation, otherwise known as the AMOC. So today I'm joined by Rita Markiner and Tilis Petit to discuss the importance of modelling the ocean. So welcome to you both. Thank you for being here today.
Thank you.
Thank you for having us.
So before we start, can you both tell us a bit about your background, so your journey to what you do today? So we'll start with you, Rita.
Okay, so I am currently a researcher at University of Oxford, and I am working on the ocean circulation in the North Atlantic Ocean and study how it responds to various processes in the atmosphere and also to what is coming to the North Atlantic from the Arctic. And in my PhD studies, I focused more on the air-sea interaction and ocean surface waves.
Cool, nice.
Yeah, and I am a researcher here at the NOC, and for my PhD I always worked on the ocean circulation in the North Atlantic. What drives this circulation, called that the Meridional Overturning Circulation, from its interaction with the atmosphere at surface to its interaction with bathymetry at depths. And for this I'm using both observations and model outputs.
Awesome. So Rita, it sounds like most of your research has always been on the ocean circulation. Can you explain what exactly we mean by that term?
So by ocean circulation, oceanographers simply mean ocean currents. But I think when this term is being used, people are mostly talking about the global ocean circulation or about some large ocean basin. And that's when we use the term circulation to describe ocean currents there.
Yeah. And is it important for our climate?
Yes, ocean circulation is very important for our climate, and ocean in general plays a very big role in regulating the Earth's climate. So, for example, over a quarter of the CO2 emissions in the atmosphere is currently stored in the ocean, as well as around 90% of the excessive heat that is in the atmosphere due to the climate change. Ocean also stores this heat as well. But apart from its role as a storage of carbon and heat, ocean also acts to redistribute this heat and carbon around. So even if we are taking the climate change aside and think about just the dynamics of the climate system, the Earth is gaining energy in the tropics from the solar radiation, and it is losing energy in the polar regions. And ocean currents, together with the atmosphere, act to redistribute this energy from the tropics towards the polar regions.
Cool. Sounds pretty vital to me. So this episode is all about kind of the importance of modelling the ocean. AMOC. So first, can you explain how would we go about creating an ocean model?
So at the most basic level, ocean models are the equations that are describing the processes that are in the ocean, and these equations relate between each other temperature, salinity, ocean density, ocean currents, and how it all changes with the moving fluid. On the more practical levels, ocean models are just thousands of lines of computer code, and this code helps to solve this equation on every grid point. And just to give you an example, the model that I'm currently working with and the configuration that is covering the North Atlantic Ocean consists of around 3 million grid points in horizontal and around 50 levels in vertical.
Wow.
So as you can imagine, to run these large models, we need supercomputers, and it takes hours to compute even 1 year of ocean circulation. And ocean models is a result of the huge amounts of effort of a lot of scientists and engineers, and it's a product of the entire institutions. And a lot of the ocean models are there in the open access, so researchers can download them, install them, and run the experiments with the models.
Wow. So there must be so many different types of different models, so researchers can kind of pick and choose which one is better for them. And I guess modelers probably use a whole range, don't they, for their
Yes,
studies?
exactly. It depends very much on the process that people are studying. So people do all types of things, from a very idealized model in very idealized configuration to a very specific, let's say, model of some particular bay and some currents that are happening in this particular location. And also there are biogeochemical models as well, so various things. I'm focusing more on the physics of the ocean, but there are various things happening, and it can be modeled in a number of different ways depending on the questions that people are asking.
Yeah, exactly. Great. So Dennis, just how important is modelling the ocean?
Yeah, well, I'll say it's very important to have model for studying the ocean, mainly because, as you well know, the ocean is vast and we cannot observe all the ocean parameters at all times from top to bottom. So that's why we really need models. We need models first to better understand the mechanisms driving this ocean circulation from seasonal to decadal or even centennial timescales. And if we are thinking more about coupled climate models, then we can also have a better ideas of the different feedbacks between the ocean, atmosphere, and even sea ice, which is very complicated feedbacks. And also, of course, we need models because it's actually the only way for us to predict what will happen in the future in terms of the ocean circulation and then in terms of climate, of course.
Yeah. Gosh, yeah, they are so important, aren't they, for so many different things. How accurate are ocean models?
That's a big question. So I would say that the only way for us to make sure that a model is accurate is by comparing it with observations. It's the only way to do. Because only observation can tell us the truth about what is actually happening in the oceans. And the good news is that the North Atlantic is one of the most observed oceans. So we have measurements of the ocean properties and currents from various ways, from hydrographic sections, mooring arrays that stays in the water for some time, from Argo floats that is drifting with the currents. You also have gliders and satellite measure of surface parameters. So in the end, all these observations are very useful and necessary to develop models and to make sure that they are accurate. And that's why it's more like what is very important is both observations and models working together.
Absolutely. So accuracy, big challenge for models. So Rita, what other challenges do you face?
So if we are talking about the North Atlantic Ocean, there are a number of processes that are currently not very well captured by the ocean models. So for example, the dynamics of the small eddies, like the eddies with a diameter less than 20 or 10 kilometers, because they are currently not resolved in most of the ocean models, and they are quite important for the density structure in the ocean and for the ocean circulation. Another process that is quite challenging to capture in the models is so-called overflows. So these are the deep currents that are creeping around the ocean bottom like a river, and then when they are crossing the underwater ridges, they form something like the waterfall. And this process is quite challenging to capture well in the models. So the models currently show too much mixing, which doesn't happen to the same extent in the real ocean. There are also some challenges around modeling the sea ice, because models have quite large spread in the way they are reproducing it. And also some narrow currents that are bringing the fresh Arctic water into the subpolar North Atlantic. Because these currents are so narrow, it's also quite hard to resolve them and resolve their dynamics correctly. So yeah, some of these processes, the representation, some of these processes is getting better when the model resolution is increasing. But the big challenge here is the amount of computer resources that is needed for it. And yeah, and in some cases, we just need more measurements to understand the dynamics of certain processes a bit better.
Yeah, of course. No, that makes sense. So, okay, switching to our main topic now. So, Tillis, can you tell us exactly what the AMOC is?
Yeah, so, well, the AMOC stands for the Atlantic Meridional Overturning Circulation, and it is part of the global ocean circulation that Rita was telling us about just before. So it is helping to redistribute the heat between the tropics and the polar regions, except that here we are focusing on the North Atlantic. So in the North Atlantic, this AMOC is characterized by an ensemble of different currents. One of them is well known, it is the Gulf Stream, but it's not only the Gulf Stream, it's really a composition of different currents that form a northward flow of warm and salty water in the upper layers of the ocean until the Arctic and non-sand part of the North Atlantic. And there, the surface water will become denser as it will become colder and fresher, and form another compensating southward flow of cold and fresh water in the lower layers of the ocean. That's, in brief, what we call the AMOC.
Great. And you mentioned earlier that the North Atlantic is one of the most observed regions that we have. So does that mean we've been able to model the AMOC well compared to other parts of the ocean?
So I think one main difficulty to model the AMOC these days is really because even if it is a large-scale mechanism, it actually involves a lot of smaller-scale processes, like, for instance, a very local interaction with the atmosphere and for the densification of the water masses, very also local interaction with the bathymetry for the overflow waters, or even very narrow boundary currents. And in the end, it's really all these smaller scale processes that are very difficult to model these days. And also maybe we have the feeling that the AMOC is difficult to model because we know that even small differences in terms of the ocean temperature, for example, between two models can lead to a large spreading of the overturning circulation now and for the future for their prediction. So maybe it's part of the story.
Yeah. And have models been helpful in AMOC research?
Yeah, I think for to study the tipping point, it has always been very useful. Even if there is a large spread also in this, for study this tipping point, but
yeah, so it helps us understand the full picture when we're kind of looking at the different regional changes and things like that. What about, we touched on it a minute ago, but what about future projections? What does model output look like for the AMOC in terms of future projections?
So climate models show that in warming climate, the AMOC is slowing down, but there is a lot of uncertainty around how much and how strong this slowdown will be. And it starts with the fact that even in climate models, even the mean state of AMOC, so even the mean strength of AMOC is quite different. So there is large spread in this regard, and also in like the magnitude of the signal of AMOC weakening. So it's quite hard to tell that, like, to which extent it will slow down in the future. There also has been some research about the tipping points and the possibility of AMOC shutting down entirely. But again, it is not quite clear yet what the conditions should be for that and whether we will approach them in the future climate. But with all of this being said, it is clear that in warming climate, the AMOC slows down.
Okay.
So yeah, this is quite robust. A result that a lot of models are showing.
And is it a model showing, because when we're talking about future projections, we're mostly talking about kind of the next 100 or so years, right? Is it showing that it's going to slow down a lot? Is there a large spread between the models? Are there any that show that it's not going to slow down, just out of interest?
There are, I think most of the models are showing that it does slow down. And I think it also, the stronger the AMOC is in the models, the more it slows down.
Yes. Okay.
Yeah. Which is, again, a lot of uncertainty around it. So we know that there is a signal, even some IPCC report is saying that there is very likely, highly likely, that the AMOC is slowing down in the future, but we just don't know quite the magnitude of this signal. Because in some models it's a little bit, and some models it's quite a lot. So
yeah, exactly. That's where the kind of uncertainty creeps in, I guess.
Yes.
And we don't know. It's the future. We're predicting the future at this point.
Yes,
so we don't
exactly. I mean, we know something, okay? It's not that we don't know anything.
Exactly. It's like weather forecast. It's like we're predicting the future. Cool. So where do you think effort should be focused for modelling the AMOC in future?
For modelling the AMOC in the future? Or
for modelling the AMOC, where should research efforts be focused in future, do you think?
No, I think it's a lot of effort is required to make sure that AMOC is modeled correctly in the future. So as we mentioned before, it is very important to continue the observations because and both observations of the smaller scale processes to make sure that models are getting them right, and also just to continue the long-term observations of how ocean circulation changes on the scale of decades and even centuries, because it will all help us to make sure, like when we have this long time series, it will help us not just to make the conclusion of how the ocean changed during this time, but also it will help us to ensure that models are capturing this longer term variability correctly as well, and hence it will increase our confidence in the model projections in the future. But as I've said before, yes, there is a number of processes that we should focus on to get the Atlantic Meridional overturning right in the models. And yes, this together with high resolution models, more observations, and this will definitely lead us to better predictions of AMOC in the future.
Yeah, fingers crossed. And maybe one for you, Tillis. Are there any regions in particular that you think we should focus on gaining more observations to help the models?
Well, I think more observations, the better it is. But I think I think it would be best to focus on these regions where the dense water is actually formed. So, of course, it is the Labrador Sea and the Erminger Seas for the northern part of the North Atlantic. But also, I think it would be good to have more observations in the Arctic because it's one of the least observed ocean. And especially for the sea ice, we don't have a good idea of what's happened in between the ocean and the sea ice. So more observations over this area would be good.
And because we don't have many observations now, I'm imagining it's a hard region to get decent observations.
Yeah,
and that's why.
It's more difficult. Yeah, exactly. We don't have always a ship to go in these regions. It's specific ships and specific instruments to measure these movements. So yeah, it's quite complicated to go.
And we've on this podcast in previous episodes we've spoken a lot about the kind of the gliders and the automated vehicles that we have. Would using those be helpful in these kinds of regions?
Definitely. It will be definitely a good idea to do that. But it's still a growing science, and
exactly.
we need to have more time to develop this.
Yeah, absolutely. So one for the kind of coming years.
Yes,
definitely
exactly.
Then. Okay, so final question that we're asking everyone in this little series. So in your opinion, what needs to happen to protect the AMOC and ensure it continues to regulate our climate? So I'll go for Vita first.
So to make sure that it acts the way it does in the present climate in the future, we need to make sure that the global warming is not so much warming, that we keep the global climate from changing too much, and we are staying as far as possible from this potential tipping point where AMOC can collapse entirely, and this will be irreversible. So even though the chances for that are not huge, but they are there. So yeah, we need to make sure that the climate change is not too strong.
Yeah. Anything to add?
I completely agree.
Completely agree. We need to just stop climate change, basically.
Exactly. Easy, right?
Great. Fingers crossed. We'll see what we can do.
Yeah.
Okay, great. Well, thank you so much both for joining us today.
Thank you.
Thanks
very much
for having us.
To find out more about NOC's research into the AMOC, or to check out the other episodes from this mini-series, visit our website, noc.ac.uk. If you'd like to listen to more of our podcasts, both seasons of Into the Blue are available on our YouTube channel on all major podcast platforms. See you next time.
AMOC.
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 AMOC. AMOC.
AMOC.
AMOC.
AMOC.
AMOC.
Hello, I'm Vivianna, and it is my honor to introduce you to Vita Sapien, an organization that seeks to bring about a global transformation. At Vita Sapien, we forge groundbreaking innovations, where eco-science meets eco-spirituality, all guided by a sustainable life philosophy. This philosophy is more than an idea. It's a growing movement to connect people through the mind and the heart to our living planet. Our research suggests that around 53 million people in the Western world alone share characteristics that we refer to as Vitan. Vita is Latin for life, so these are the life people. Specifically, life people love nature, trust science, and take action to make things better. Does this sound like you? What is missing, we believe, is a unifying philosophy that can help amplify the impact of life people in fostering a civilization that thrives with nature deep into the future. This sustainable life philosophy is called Vita Worldview, and it contains unique concepts that will help us weather this new age of global crisis and prevail beyond. Together, we can cultivate the blossoming of a remarkable era, the Verdant Age. The Verdant Age is not a dream. It is a potential reality. It is a future where humanity and the living planet thrive together in harmony, stretching deep into the long future. This is not just survival. It is flourishing for millions of species, for billions of people, for millions of years. At Vita Sapien, we believe that our birthright as humans is to thrive on Earth, and that the climate and ecological crises of today are not the end. They are merely challenges, stepping stones to something far greater. For nature lovers who respect science and take action, this is your time to shine. And Vita Worldview is a guiding light toward the main prize, the longevity and health of people and our beautiful living planet. Please take some time to familiarize yourself with Vita Sapien organization and Vita Worldview. Thank you.